A warm welcome once again. The Department of Chemistry at the Ramapuram campus, established in the year 2004, is focused on imparting knowledge in the applied aspects of chemistry to the budding engineers through quality teaching, besides promoting research activities and consultancy. Highly qualified and dedicated faculty members are the backbone of the department. Faculty members have published 80 papers in SCI and Scopus indexed journals in the last 5 years. The department also has tie-ups with recognized institutions and R&D laboratories for research activities. The Department of Chemistry, as part of the esteemed institution of SRM IST Ramapuram, extends its beautiful and benign welcome to the 2-day international conference in collaboration with the Association of Chemistry Teachers, Mumbai. Coming together is a beginning. Keeping together is progress. Working together is success. Darkness and dawn come together to augment the new day. A conference is a conglomeration of academicians where healthy discussions lead to great decisions. No grand idea was ever born in a conference, but a lot of foolish ideas have died here, to quote the words of the theorist Scott Fitzgerald. Though the quote professes to be funny, there is truth in it too. Real progress, real growth comes only when the irrelevant and the insignificant are eliminated. Welcome you all to the ANRF sponsored 2-day international conference on smart materials for innovation in low carbon energy and environment, shortly termed as SMILE 2025. Wow, what is such a pretty name ever thought out for a conference that deals with the most complex subject ever in any phase of education. Welcome you once again. A warm welcome to the esteemed chief guests, heads of institutions, heads of various departments, faculty members from other institutions, faculty members of SRM family, enthusiastic research scholars, participants and paper presenters who have joined both online and offline. The meeting of personalities is like the contact of two chemical substances. If there is reaction, there is transformation. Yes, whenever great minds meet up, there is always the transformation of the best kind to make the morrow worthwhile. This again is the version of Carl Jung's quotation. Any endeavor begin with a prayer, no doubt culminates in progress, and let us now invoke the blessings of the Almighty to bestow His serene blessings on the momentous day. Let us now rise in our seats for the Tamil Thai Vaalthu.
நீராறும் கடலுடுத்த நிலமடந்த கெளிலொழுகும் சீராறும் வதனமென திகழ்பரத கண்டமிதில் தெக்கணமும் அது சிறந்த திராவிடனர் திருநாடும் தக்க சிறு பிறை நுதலும் தரித்தனரும் திலகமுமே அத்திலக வாசனை போல் அனைத்துலகும் இன்பமுற எத்திசையும் புகழ் மணக்க இருந்த பெரும் தமிழரங்கே தமிழரங்கே உன் சீரிலமை திறன் வியந்து செயல் மறந்து வாழ்த்ததுமே வாழ்த்ததுமே வாழ்த்ததுமே.
Light is the shadow of God. In the right light, at the right time, everything becomes extraordinary with the touch of the divine. Let divinity be lit in the Kuthuvilakku. I request all the dignitaries to join for the same. Any one of the participants can come onto the stage to join here. One of the participants, or one or two, can be coming onto the stage. Please come. Thank you, everyone. I now invite the head of the Department of Chemistry, Dr. Helen P. Kavita ma'am, the convener of the conference, to exude the warmth of hospitality by way of a welcome address, followed by the brief overview of the conference.
Distinguished guests on the dais, respected speakers, esteemed researchers, heads of the institutions, heads of various departments, faculty members, participants, and my dear students. A pleasant morning to one and all gathered here. It's my proud privilege to welcome you all for this international conference on smart materials for innovations in low carbon energy and environment, SMILE 2025, organized by the Department of Chemistry, SRM IST Ramapuram, in association with the Association of Chemistry Teachers, Mumbai. As we begin the conference, it is fitting to reflect on the broader global vision, that is United Nations Sustainable Development Goals. Dear participants, the progress of a nation is measured not only by the economic growth, but also by the well-being, equity, and the environmental sustainability it provides to its people. When we talk about the Sustainable Development Goals, out of 17 Sustainable Development Goals, 4 are of paramount importance, especially with respect to life and growth. SDG 6, which talks about clean water and sanitation. SDG 7 is about affordable and green energy. SDG 12 is for responsible consumption, and SDG 13 talks about the climate change. Albert Einstein once said, "We cannot solve our problems with the same thinking we used when we created them." Dear friends, today's world stands at a critical juncture, facing escalating energy demands and unprecedented environmental challenges. Only with innovative thinking, scientific advancement, and global collaboration, we can pave the way forward. And sustainable materials are at the forefront of this transformation, whether it is advanced batteries or supercapacitors, thermoelectrics, photocatalysts, or intelligent polymer system. And these materials are redefining the efficiency, sustainability, and environmental stewardship. Over the next 2 days, there will be insightful lectures and vibrant discussions on the smart materials for energy and environment. And we are very happy to organize this international event in association with the Association of Chemistry Teachers, Mumbai. As usual, we get overwhelming response for this 2 days international event. We have received around 200 papers, and out of which 160 papers have been selected for various oral and poster presentations in 8 parallel sessions for these 2 days. And a book of abstracts will be, with ISBN number, will be released today. And the selected papers, after scrutiny, will be published in Scopus Index Journal. On this auspicious occasion, it's my honor and privilege to welcome all of you for this international conference. First of all, I would like to welcome our respected chief guest, Dr. V. Jayaraman sir, Director, Materials Chemistry and Metal Fuel Cycle Group, IGCAR Kalpakam, a learned scientist and an efficient administrator. I always admire him for his simplicity and humility and unwavering commitment to professional ethics. Sir, we are really honored to have you here this morning, and I welcome you, sir, on behalf of the Department of Chemistry and ACT. And it's my honor and privilege to welcome the guest of honor, globally renowned as the father of green chemistry, Professor John C. Werner, President Technology Greenhouse USA, Distinguished Professor of Green Chemistry, Monash University, Australia, and co-founder of Beyond Benin. Sir is joined online. And Professor Werner has transformed the way the world looks at chemistry. And he has groundbreaking work in formulating the 12 principles of green chemistry has provided a scientific framework that guides industries, researchers, policy makers towards safe, cleaner, and more sustainable chemical processes. We are really honored to have Professor John Werner with us today. Welcome you, sir, on behalf of the Department of Chemistry and on behalf of the Association of Chemistry Teachers. Ratish sir, join Dr. Ratish, check. It's my honor and privilege. He said he'll be joining online. Check with us. It's my honor and privilege to welcome Dr. R. Ratish, Director General, Center for Materials for Electronics Technology, CMET, under Ministry of Electronics and Information Technology, Government of India, Pune. I know Dr. Ratish as a man of simplicity and integrity. He is renowned nationally and internationally for his exceptional contributions to advanced materials and emerging technologies. Welcome you, sir. Happy to see you online, sir. His visionary leadership has elevated. Sir, can you able to hear me, sir? Yeah, sir. Thank you, sir. Thanks. His visionary leadership has elevated cement stature and strengthened India's scientific presence on the global stage. We are really honored to have you here this morning, sir, and we welcome you, sir, on behalf of the Department of Chemistry and on behalf of the Association of Chemistry Teachers. It is my honor and privilege to welcome our esteemed Registrar of SRM IST, a dedicated and a visionary administrator. He is known for his strong commitment to the institution. He is known for his exceptional work ethics, unwavering support for the faculty and staff. Despite his distinguished role, he remains remarkably simple and approachable. We are really honored to have you here this morning, sir, and we welcome you on behalf of the Department of Chemistry and ACT. It is my honor and privilege to welcome our respected Dean, Dr. Sakti Ganesh, sir, a dynamic and a visionary leader, a leader who is instrumental in driving innovation, a leader who is strengthening the research culture and setting new milestones in the growth of SRM Ramapuram campus. And on behalf of the Department of Chemistry, I extend a very warm welcome to you, sir. Thank you, sir, for all your support you are extending towards our department. And it's my honor and privilege to welcome Professor D.V. Prabhu, President of Association of Chemistry Teachers, with whom we are organizing this event. Professor Prabhu, sir, is a very dynamic and inspiring leader. He has carried ACT to greater heights, taking chemistry education and outreach across the country and above and beyond. His dedication and passion for chemistry have deeply enriched the chemistry community. We are very happy to organize this conference along with ACT, sir. Thank you for your presence, and also acknowledge the presence of Mrs. Prabhu, sir. Mrs. Prabhu here. Thank you, ma'am, for honoring our conference. And it's my proud privilege to welcome our distinguished speakers for this 2 days international conference. I kindly acknowledge the presence of Dr. V. Ganesh, Senior Principal Scientist, Sikri Karekudi, Dr. W. B. Gurnale, sir. Welcome you, sir. Visiting Professor, RTM Nagpur University, Nagpur. Dr. Shankara Radhakrishnan, ma'am. Welcome you, ma'am. She is from University of Pretoria, South Africa. Dr. Venkateshwaralu Mannu. Welcome you, sir. Scientific Officer, Midwest Advanced Materials and Energy Private Limited. And Dr. Sri Ranjani Arumugam, Director of Administration, XC Germany. Dr. Aravindan Isar Tirupati, who will be joining tomorrow, and Dr. Ganesh Pawar sir, Principal, Dalmia College of Arts and Science, Mumbai, and Professor Brahmananda Rao, Dean, Material Chemistry and Metal Cycle Fuel Group, IGCAR Kalpakam, who will be joining tomorrow, Professor Kodandaraman, IIT Madras, Dr. Ravi Kumar, Climate Researcher from Hyderabad, and Professor Brijesh Pare, Professor and Head, Madhav Science College, Ujjain, and Dr. Abba Bharati, co-founder of CTO, Saratech Innovative Technology in Chennai. And I welcome all the session chairs who are the juries for various oral and poster presentations. I wholeheartedly welcome the Vice Principals, Deputy Dean, School of Computer Science and Engineering, heads of all the departments, faculty members, and participants. I wholeheartedly welcome all the participants who are from different institutions across the different parts of the country and abroad, and welcome the participants from Germany, France, USA, South Africa, Oman, and Malaysia, and China, who will be presenting their work in an online mode. Before concluding, I just say, when we conceive the title for the conference, we firmly want to have the acronym SMILE, because SMILE always gives hope. A hope for green and energy, a hope for green environment, a hope for a greener planet. So I welcome all of you with a bright smile, and I welcome all of you to be a part of SMILE. Thank you so much.
Thank you, dear ma'am, for a very warm welcoming note. As the host institution of the conference, it is time now to honor our guests. I now humbly request our esteemed registrar, a man of inspiration and wisdom, to honor our chief guest. Thank you, sir, for the benevolent gesture. I now invite a man of futuristic vision and vibrance, our respected Dean ENT, to honor the President of ACT, Professor Dr. D.V. Prabhu. Thank you, dear sir. I now invite the President of the Association of Chemistry Teachers to give a glimpse of how ACT works to promote research pursuits in the field of chemistry. Welcome you, sir.
All the dignitaries on the days, dignitaries in the audience, Professor Helen Kavita, convener of SMILE 2025, eminent invited speakers, distinguished invitees, delegates, students. A very good morning to all of you. On behalf of the Association of Chemistry Teachers, it is my privilege to welcome you to the International Conference on Smart Materials for Innovation in Low Carbon Energy and Environment, organized in the beautiful campus of SRM Institute of Science and Technology under the inspiring leadership of Professor Helen Kavita. The topic for the conference is very timely because all over the world we are talking of sustainability, green chemistry, green principles, so on and so forth. And in India, we are having a large number of people working in the field of green chemistry. The Association of Chemistry Teachers was started way back in 2000, thanks to the initiative taken by the Homi Bhabha Center for Science Education, TIFR, and it is celebrating its silver jubilee year this year. A large number of programs have been organized all over India, in the small towns, in the big cities, and some of our activities were national and international conferences, training workshops for teachers and students, then a national convention of chemistry teachers, research convention, concept test in chemistry for BSc students. It is the only test for BSc students in our country. Celebration of National Chemistry Day and National Science Day. Publication of a ACT newsletter with Professor Vasudev Gurnole as the chief editor. We are actively involved in the Indian National and International Chemistry Olympiad program right from 1999. And the performance of the Indian teams all these years has been exemplary. All our students who have represented India at the International Chemistry Olympiad have won medals, either a gold medal or a silver medal or a bronze medal. One of the important activities in collaboration with IUPAC is the Global Women's Breakfast, which is held every year in February. The IUPAC organizes this activity worldwide, and in India, our association is supporting this activity and propagating it in different parts of our country. Professor Vijendra Singh is the national coordinator of this very unique activity. Now, this breakfast is a very unique activity wherein on a particular day in February, women scientists and teachers all over the world organize chemistry activities for students and teachers. And I am very proud to tell you that for the last 5 years, the maximum number of activities have come from our country. Last year we had 80 entries, which is the highest in the world, far ahead of USA, Japan, Europe, etc. And this is a tribute to the chemistry teachers and scientists of our country. The forthcoming breakfast is on February 10th, 2026, and I would appeal to all the teachers to organize some activity connected with chemistry. It can be a conference, it can be a workshop, it can be a talk, it can be an exhibition, anything related to chemistry. Every year we give 12 ACT awards to the distinguished teachers of our country to recognize their valuable work towards teaching and research. We collaborate with the international organizations like the Royal Society of Chemistry London, IUPAC, and the Indian Chemical Society. We operate through 6 zonal councils, and I am very happy to tell you that South Zone is one of our most active zones in our country. And it is a tribute to the chemistry teachers of the South Zone. And I must mention Professor Helen Kavita, Professor Mannam Krishnamurthy, and Professor M. Swaminathan, who are leading this movement to organize chemistry activities in this part of our country. So I would like to thank them for their active involvement in chemistry activity. We have more than 3,000 life members and 21 institutional members from academia and industry, and some of the most distinguished scientists and academicians are our patrons and sources of guidance and support. I must mention Bharat Ratna Professor C.N.R. Rao, the former advisor to the Prime Minister of India, and Professor John Warner, the father of green chemistry, along with Professor Paul Anastas. Professor Warner and Anastas formulated the 12 principles of green chemistry way back in 1998. And he was here in in October, where I met him, and I invited him to give a talk in this particular conference. He regretted his inability to come personally, but he said, I will give an online lecture, which we will hear a little later. I am grateful on behalf of ACT to the management of SRM IST for providing all facilities for this conference. ACT is grateful to Professor Helen Kavita and all her colleagues for their dedicated efforts to plan and organize this international conference on such a grand scale. A special word of thanks goes to our guest of honor, the father of green chemistry, Professor John Werner, who will deliver his talk sometime later. I urge all the teachers in the audience to become life members of ACT. The forms are with me, and take part in our activities. I wish the conference grand success and all the participants, particularly the students, fruitful interactions with the eminent faculty of the conference. With these few words, I wish you well 2 days of good interaction. Thank you.
Thank you, sir, for giving a crystal clear account of the proceedings of ACT to the audience to keep them inspired and motivated to explore further in the future. I extend my warm welcome to the Dean ENT, a man who always bespeaks his deeds to give his felicitation note on this great eve.
Very warm good morning to one and all present here. First of all, I appreciate the entire team of chemistry department for organizing such a wonderful conference. In a short span of time, they made it very successful. Let's give it a big round of applause. So there have been a lot of positive notes here. Again, from my philosopher used to say that positivity may not be leading to success, but negativity surely leads to failure. At least we are trying positivity here. Let's hope this conference will be a grand successful. First of all, I thank our chief guest today, Dr. V. Jayaraman, who accepted our invitation and came here for honoring us. And our guest of honor, John C. Werner, who is attending online and will be giving a session as a presidential note. And our guest of honor, Dr. R. Ratish, and recently you spoke about the convener, Dr. Prabhu, and our beloved Honorable Registrar, sir. So, talking about Registrar, sir, whom I inspired a lot, because if you're able to handle the pressure, you will be a successful leader, right? I have seen numerous occasions where he's had a lot of pressure and he doesn't show it a big show. He'll just smile. That's what this conference also symbolizes, that with a short note smile, right? You keep it very simple. I want to add an analogy to that. When you'll become a smile, when you give a small kiss to it. Kiss is not other kiss. Kiss is like keep it simple to be a successful. So that's what this conference is, smile with a kiss. So join together, it being successful. Again, we talk about more about low carbon energy and environment. We talk about more sustainable development, SDG goals, and in all the various 12 goals of like water goal we go into drive it upon. And every month we take it to one private goals to that for our institution, and we're working on that. And every month we used to follow that one. It's not only practice, we don't preach, and as well as we practice too. So again, in the universe, everybody talks about low carbon and environment, keep it environment very clean and green. First of all, when we practice it and when we preach it, we have to do it by our own, right? That's the ultimate aim of every individual. And whether we are using what kind of car, whether our house is solarized, and how many energy consumption we do it, because energy neither be created nor be destroyed as per Newton Law 3. Whether we are utilizing properly or not, that's very, very important. The basic principles of low carbonization energy environment we have to taken care. In all the classrooms we have to start with, and as an individual we have to start with. That's very, very important. And always I used to say that there is a lot of difference between a technical traits and a practical traits. How a student understand, how a faculty conveys to a student is very, very important. I used to say a small analogy when I was taking a lecture in a small classroom for a 6th standard kids. I asked a small question, right? So you have a 2 orange and 2 orange is equal to what? The small kid said, I have 4 orange. Then other kid, when I asked 2 lychee and 2 lychee equal to what? And the kid said it is 5. Then maybe my mathematics is wrong. Again I asked, you have 2 apples and 2 apples equal to what? She said 4. Again I came back to the same question. You have 2 lychee plus 2 lychee is equal to what? She said 5. Then I asked how come? She said 1 lychee is in my bag, sir, so totally it's 5. So technically I might be right, practically the student might be right? So there's a huge difference what we teach and the understanding level between the students and how we're going to communicate, very, very important. And that's what our professors do, we believe, and we have a lot of knowledge session is happening. Whether knowledge leads to implementation, that's very, very important, because you might be having good knowledge. If you fail to implement it, probably your knowledge level is going to be volatile. And if you see, again, we do a lot of things in a campus. We might be doing good things, but we not be doing great things, right? So good is the enemy of great. So how it's going to bring this black box to be together? So disciplined thoughts, disciplined behavior, and disciplined attitude makes a lot of difference when you transform from good to great. And if you be nice, right? Probably we have nice people with us. We have nice human being with us. We are doing nice things with us. Probably you might be liked by many people, but you recently will be forgettable. But if you do successful, right, you will be remembered for a lot. I believe this one of the conference is one kind of it. Probably will succeed by bringing low carbon energy and environment to our campus as well as to the global, by bringing a lot of knowledge transfer which leads to implementation. Thank you so much.
Thank you, sir, for striking the very key note of the conference in your insightful felicitation address. Now, I request our respected registrar to confer the presidential address of the day. Over to you, sir.
A very good morning to all of you. Esteemed Chief Guest, Dr. V. Jayaraman, Group Director, IGCAR, Dr. Ratish, Guest of Honor, Distinguished Professor John C. Warner, Learned Professor Dr. D.V. Prabhu, President, ACT, Dr. Satya Ganesh, Dean, Engineering Technology, convener of this conference, Dr. Helen Kavita, other colleagues on the dais and off the dais, distinguished researchers, faculty members, and my dear students, once again, a warm morning to all of you. Indeed, it gives me a great pleasure in participating in the international conference on smart materials for innovation in low carbon energy and environment 2025, organized by the Department of Chemistry, Ramapuram campus, in association with the Association of Chemistry Teachers, Mumbai. Friends, at SRMIST, we strongly believe that academic institutions have a profound responsibility toward the environmental protection, societal well-being, and sustainable technological development. Our university has consistently aligned its research, outreach, and innovation ecosystem with the global goals such as the UN SDG, Sustainable Development Goals, particularly those focusing on clean energy, responsible consumption, climate action, and environmental resilience. Through its state-of-the-art research facilities, green campus initiatives, and interdisciplinary collaborations, SRMIST strives to be a leader in shaping a cleaner and more sustainable future. To the external members of the conference, I would like to convey this point. In the recently declared NIR of 2025, we stood in the 4th position for the various SDGs activities in the country. Out of 1,400, 500 universities, we are in the 4th position. We are doing lot of activities across all the campuses, as mentioned by our Dean, Faculty of Engineering and Technology. And also we are doing good research in the university. We are ranked 25th among the various institutions in the country in NIR 2025. Also in innovation, we are in the band of 11 to 50. The total number of Scopus indexed publication in 2024 was 8,660 across all disciplines, and in 2025 so far 7,836 articles have been published with Q1 journals, accounting for 41.3% in 2024 and 44% in 2025. Q2 publications stands at 23.7 in 2024 and 26% in 2025. Out of the total number of publications in 2024 and 2025, international collaborations contributed significantly with 27% of publications in 2024 and 24.2 in 2025. And also the H index of all the publications from all the databases has increased from 160 to 180 in 2025. And faculty members from SRMIST have also published high quality nature indexed articles with 47 publications in 2024 and 52 in 2025. And friends, we have been doing lot of support to all our faculty members in different form in terms of research incentives and for the faculty members and students, PhD scholars, and not only that, we provide a stipend for the PhD scholars every month. And we are also spending approximately 7 to 8% of total income for the research. So lot of initiatives are being taken in terms of research, and always all our research focuses on the various SDGs. Of course, today's conference, SMILE 2025, focuses on an issue that is vital to worldwide scientific and societal goals. Nations worldwide are facing an unimaginable energy crisis. Rising energy demand, along with the limited availability of fossil fuel reserves, has resulted in a growing imbalance between consumption and sustainable supply. This imbalance is driving economic instability, geopolitical tensions, and constraints on industrial growth. Above all, our dependence on conventional energy sources has triggered serious environmental consequences, global warming, biodiversity loss, extreme weather patterns, declining air quality, and degradation of water and soil systems. I am happy to note that several specialists from academia, industry, and international research centers are delivering plenary talk in the 2 days conference. I extend my sincere appreciation to the convener, organizing committee member, faculty members, and the student volunteers whose hard work to make this event possible. Especially, I appreciate Dr. Helen Kavita and her team for bringing out such kind of activity in the institution. I also express gratitude to the keynote speakers, resource persons, and international delegates who have joined us to share their expertise. Your participation enriches our academic environment and strengthens our collective efforts towards developing sustainable, low-carbon solutions. I encourage all participants to engage actively in the sessions, exchange ideas, and explore opportunities for collaborations. The challenges before us are complex, but with the shared knowledge, scientific integrity, and a commitment to innovation, we can contribute to building a cleaner, greener, and more resilient world. I wish the conference a great success. Thank you very much. Thank you for this opportunity.
Thank you, sir, for a profoundly thought out, well organized, and earnestly expressed presidential address, throwing light on the strength and quality of research contribution of SRM faculty fraternity. I now request Dr. K. Hema, Assistant Professor of Chemistry, to introduce the guest of honor who has joined online, Dr. R. Ratish, CMET Pune, to the gathering.
Good morning, one and all present in this gathering. It's my pleasure to introduce our guest of honor, Dr. Ratish, Director of CMET Pune. Sir is a well-known scientist in microwave ceramics, electronic materials, and e-waste management. And Sir has received prestigious international fellowships such as Alexander von Humboldt Fellowship, Germany, Boys Cast Fellowship, USA, and Lady Davis Postdoctoral Fellowship, Israel. Sir has also been honored with national awards, including Elsina EFI National Award for Excellence in Electronic Materials Hardware Manufacturing, and the PSN National Technology Award and Young Scientist Award from the Government of Kerala. Sir is a life member of the Material Research Society of India. Sir has made significant contributions to materials for NAVIC and GPS antennas, low-loss dielectric substrate, and advanced ceramic technologies. He has many research publications, patents, and lead major national projects, including the Center of Excellence in E-Waste Management, funded by MITI and the Government of Telangana. We are honored to have him with us today. Ladies and gentlemen, please join me in gathering Dr. R. Ratish to deliver the guest of honor address. Thank you.
renewable sources is one of the important for wind energy. You require almost 500 kilograms of common NTFEB permanent magnet. The country doesn't produce single kilogram of NTFEB magnets at the moment. More than 92% of the imported NTFEB magnets they imported from China. And almost 3 months back, China electric vehicle, it uses 2 to 3 kilograms of permanent magnet. The country, if I look at excellence, we have self-sustainable ecosystem. Towards self-sustenance in critical materials, especially for such kind of renewable materials required for renewable energy. So government has also initiated PM Kusum scheme, PM Surya Ghar scheme, and all that to improve the production of renewable energy. But the problem, as I pointed out earlier, many of the critical materials for renewable energy, for example, if you want to make electronic grade silicon, one of the very important requirement is polysilicon. Without polysilicon, we cannot produce silicon wafers and translate them into solar cells or even semiconductor materials. We don't have a facility for production of polysilicon in the country, and I already touched upon permanent magnets. So similarly, there are many other materials, for example, gallium and germanium, two important materials for the production of semiconductors. 1 trillion semiconductors are produced worldwide. That means 150 semiconductors per every human being in the world. But the problem is, unfortunately, India doesn't produce commercial semiconductors. The importance of semiconductors in this low carbon energy emission, you may be wondering, because if you have a 7 nanometer semiconductor and a 10 nanometer semiconductor, you will have 40% of energy efficiency in your mobile phone if you use a 7 nanometer semiconductor. So I feel that we need to work on such kind of indigenous vision on smart materials. Professor Helen has already touched upon what are the materials which are fall under that. There are many materials like materials for hydrogen generation. You need supercapacitors, you need lithium and different kind of lithium and battery chemistries, and many other materials for this particular ecosystem. Now, coming back to our excellence in research in this line, as you know that India is the 35th rank in global bold innovation. So actually this is a very good, achievement, I would say. World Innovation Index, we were only at 48th place in 2020, whereas there is a leap increase by 2025, where we are at the 35th position.
So in CMET, I come from CMET, this Center for Materials for Electronics Technology. We are under Ministry of Electronics and Information Technology. We do a lot of efforts in bringing materials for renewable energy. One of the program which we are envisaged is that production of NdFeB magnets, not from primary materials alone, but we also do, from the secondary raw material, because the buzzword now is resource efficiency and circular economy. There is a very big program which is implemented in Europe called a Sustainable Magnet Program. We collect all end-of-life magnet and we recycle it. Recycle means so we do using hydrogen degradation, we convert NdFeB into powder and then convert it into new magnet. Maybe 20 to 25% is the total magnet requirement in the country can be met from that. Also, we work on all kind of ultra high purity materials up to 7N purity for semiconductor applications. And another interesting, exercise which we have done in this line is to establish country's first center of excellence on e-waste management. As you're aware, 62 million tons of e-waste is produced globally, which contains almost 65 billion, worth the secondary raw material. India is again the third largest users of such raw materials, and we have established a center of excellence which recycle all value chain, from whether it is lithium-ion battery, printed circuit board, silicon solar cell, permanent magnet, liquid crystal displays, and so on and so forth. Just to cite an example, if from lithium-ion battery alone, end-of-life lithium-ion battery alone, we take out lithium, cobalt, manganese, and nickel, and we produce new batteries out of that. And we have transferred this technology to almost 30 industries towards resource efficiency and circular economy. And I am very happy that Professor Dr. V. Jayaraman is also available with us, who also heads materials characterization and recycling. I feel that there is a lot of potential in small, reactors, modular reactors, where which can be deployed in remote areas for a generation of electricity. But I'm very happy that BRC, or Atomic Energy, has started efforts to bring out this kind of innovations in the country. I also urge, Professor Jayaraman and his group that there should be a drive for immobilization of, nuclear waste, especially after Purex process, or whatever kind of, high-level nuclear waste which is coming out. I think that is an area where the country can really focus upon. Through materials like hollandite and things like that, we can immobilize them in tunnel cavities and things like that. I think we need to look at all those things. So because of the paucity time, I conclude here. Thank you so much once again for, making me as a part of this particular program. All the very best for the conference, and thank you so much. Jai Hind.
Good morning, all. It gives me great pleasure to introduce a distinguished scientist and an inspiring role model, Dr. V. Jayaraman, Director of Material Chemistry and Metal Fuel Group at the Indira Gandhi Center for Atomic Research, IGCAR, Kalpakkam. Dr. Jayaraman began his scientific journey by completing his PhD from the IISc, Bangalore, after which he joined IGCAR in 1989 as part of the 32nd batch of BARC training school. Since then, he has devoted more than 3 decades to research and development in nuclear materials, fuel chemistry, and advanced technologies that supported India's fast reactor program. His work focused on developing advanced materials and metal fuels, studying their behavior under extreme conditions and creating innovative chemical sensors and pyrochemical aquatic fuel cycle process that ensure safer and more efficient reactor operations. Dr. Jayaraman has authored over 140 research papers widely cited in international scientific literature, reflecting his strong impact on nuclear science, material chemistry, and fast reactor fuel technology. In recognition of his outstanding scientific contribution, he received the Homi Bhabha Science and Technology Excellence Award, one of the highest honor in India's atomic energy research community. Beyond his leadership roles, Dr. Jayaraman has made several professional and scientific contributions of national importance. Dr. Jayaraman also serves as a professor at Homi Bhabha National Institute, where he mentors and guides young scholars to pursue research at the frontiers of science. His ability to combine deep scientific insights with clarity, humility, and passion for learning makes him an inspiration to every student. We can draw inspiration not only from his academic achievements but also from his dedication, curiosity, and commitment to advancing science for the benefit of the society. All of you, please join me in welcoming our chief guest, Dr. V. Jayaraman sir, to deliver his guest of honor speech.
Thank you, Madam. Respected Professor Ponnuswamy, Registrar, SRM Institute of Science and Technology, Dr. Sakti Ganesh, Dean, Engineering and Technology, SRM IST, Dr. Ratish, who had joined online and guest of honor of this day, SMILE 2025, and Director General of Center for Materials for Electronics Technology, shortly CMET Pune, Professor John Warner, who joined online, guest of honor for SMILE 2025 and President, Technology Greenhouse USA, and Distinguished Professor of Green Chemistry, Monash University, Australia, Professor Prabhu, President, Association of Chemistry Teachers, Mumbai, and convener of SMILE 2025, Professor Helen Kavita, Head Department of Chemistry and convener of SMILE 2025, faculty members on the dais and off the dais, dignitaries, invitees, and participants of SMILE 2025. A very good morning to all of you and good wishes for the rest of the day as well. It is indeed a honor to participate in the inaugural session of this conference, International Conference on Smart Materials for Innovation in Low Carbon Energy and Environment, shortly SMILE 2025. Just a piece of data to all of you. All of you are aware that the present carbon dioxide level in our atmosphere is about, any students who can answer this? Don't see your mobile, just tell the answer. It's around 420 parts per million, ppm shortly, today. What was its value about 125 years back? That is beginning of the last century. What was the number? Any guess? It was just half of it. That is 200 ppm only. That is, in about 125 years or so, we doubled the carbon dioxide concentration in the atmosphere by human activities. Now, what is the reason for this? Of course, massive industrial revolution is attributed to the enhanced carbon dioxide evolution. Apart from carbon dioxide, what are the other species we normally worry about? From your automobile exhaust, we get good amount of oxides of nitrogen, shortly NOx, oxides of sulfur, shortly SOx, chlorofluorocarbons. Where are they used? In refrigerator. Of course, we cannot use them right now in refrigerators. These are also getting added to the atmosphere. This is one scenario. What is a scenario that is also going on parallelly? The world population has also grown up from a level of 2 billion, which was in the beginning of 20th century. That is, in 125 years back, we were about 2 billion. And what is the number today? Students? It's 8 billions. That means we have increased by 4 times, and also we have increased the carbon dioxide level by 2 times in 125 years. Of course, this calls for massive expansion of agricultural produce, healthcare, electricity production, transportation, building infrastructure, that is like houses, etc., to people. Thus, please note, we are caught up between huge population on one side and the industrial growth on the other side, which is the cause for all this pollution. What is the impact of industrial revolution and other activities, other human activities? Presently, we are aware that some of the islands in the Pacific Ocean are at the verge of inundation. A small island in Pacific Ocean by name Kiribati. Its president made a tearful request in Paris conference that for no fault of them, their country is getting inundated in water, that is immersed in water. After some years, they will become refugees in other countries for no fault of them. It's a matter of time that cities like Chennai, Mumbai, etc. may also vanish from the map. Please note this. We also hear and read about jargons or phrases like climate change, zero carbon, etc., etc. Do we have a solution for all these problems that are being posed to us today? I have a thought, and one of the direction can be as follows. It is interesting to understand how nature accomplishes every process with optimum energy utilization. In other words, all the processes take place at room temperature, atmospheric pressure, and within small span of time also. It also does not generate waste. On the contrary, the byproducts generated by plants are benign. You know about photosynthesis. What is photosynthesis? In photosynthesis, plants use carbon dioxide from the atmosphere, and using chlorophyll, food is produced for the entire world. The process utilizes carbon dioxide from the atmosphere and releases oxygen back to the atmosphere, a product which we want. Thus, cleanses the atmosphere in a very natural way. Further, we know that even the waste generated by living beings, including us, are used as manure to the plants. If we make an attempt to mimic nature, that is, plants produce food by consuming carbon dioxide, this food is consumed by us, and the waste generated to the process, from the process, goes back to the plant. All these events are occurring in a cyclic fashion, and the food chain is sustained. So, this is what we may have to think now. Then, addressing to Dr. Ratish's point on small modular reactors, yes, it's a technical jargon that is posed to our country, because India is becoming or emerging as one of the stakeholders of nuclear energy. So, as a result of this, many foreign countries are requiring us to buy their reactors in our country and generate power. Also, India doesn't want to do all these things just by buying things from abroad and become slaves of those countries. We also want to develop technologies for small modular reactors, which can be put amidst public locations, like places like Chennai, even in T Nagar. It's the most populated locations in Chennai. We can have a reactor to produce energy. Anyway, India, our country is looking forward towards that. And coming to the point of the waste generated from nuclear reprocessing. Actually, now the word waste itself should be removed. I just want to tell you all know, in the nuclear reaction and power is generated, waste, that is fission products, are also formed, because a bigger nuclei becoming a two smaller ones with generation of further neutrons, and these neutrons sustain the nuclear chain reaction. Now, these fission products are radioactive. If we do the reprocessing, we can separate these fission products from the useful uranium and plutonium. And if you want to store it as such, then we may have to do the surveillance for these ways about 2 million years. Now, if you remove the useful uranium and plutonium and also americium from this, the surveillance time comes down to 10,000 years. And of course, if you separate fission products like cesium and strontium, you know these two radionuclides are useful for societal application. So cesium can be used for blood irradiation and other therapeutic applications. Anyway, strontium, as Dr. Ratish and others in the audience are aware of, it is being used as a radio thermoelectric generator, which is used in deep sea missions or deep space missions as well. So if you could separate all these things, and also I tell you, we all know precious metals in the periodic table. Which are they? Palladium, rhodium, ruthenium. Rhodium chemistry is very, very rarely known, you all know. Palladium is getting depleted because it is being used in most of our catalytic converters, including our cars, vehicles, etc. It is getting depleted in the earth crust. What is a way out? In the nuclear fission, you produce good amount of palladium. It is slightly active. If you find methodologies to separate this palladium, it can be again used for societal applications. So, thus, I strongly believe that chemists have a great role to play in all these endeavors, which can occur in and around ambient conditions and also other materials that can be produced. The smart word is referred to that only, which is significantly in great demand today. I am sure that this international conference on smart materials for innovation in low carbon energy and environment, shortly SMILE 2025, will provide the necessary platform towards this endeavor. Further, I congratulate SRM IST for choosing this very important topic as a theme of this event at this crucial juncture. I wish all the participants fruitful deliberations. Thank you. Jai Hind.
Thank you so much, sir, for a very relevant deliberation tailored to mark the central theme of the conference. It is time now to pay our attention to the most exalted moment of the summit. The proud release of the souvenir as the epitome of success is set aflame. I request all the delegates to gracefully accept the souvenir as the testimony to the perfect execution of the intent, more contemporary and even challenging. Thank you, everyone. As the befitting closure, we have the guest of honor, Professor John C. Warner, USA, who has joined online to give his interesting discourse and ignite the fervor of research amongst the young aspiring engineers. I now request Dr. P. Aarti, Associate Professor of Chemistry, to introduce Professor Warner to the gathering.
It is my great privilege to introduce the visionary scientist and one of the founding architects of green chemistry, Dr. John C. Warner. Dr. John C. Warner, President and CTO of the Warner Babcock Institute for Green Chemistry, is a globally celebrated founding pioneer of green chemistry. He co-authored the landmark test that established the field and developed the 12 principles of green chemistry, shaping sustainable chemical practices worldwide. He holds a PhD from Princeton University and began his career at Polaroid, later serving as a tenure professor at UMass Boynton and UMass Lowell. Dr. Warner co-founded Beyond Vinyl, a leading organization for green chemistry education. A prolific inventor with nearly 215 patents, his innovation span organic synthesis, polymer photochemistry, non-covalent derivatization, and entropic materials design. He has collaborated with more than 100 Fortune 500 companies, contributing to technologies such as the DS Parley Ocean Plastic Shoe and several successful startups. His achievements have earned major honors, including the Passman Award, Perkin Medal, ACS Fellowship, and recognition as one of the 25 visionaries changing the world. The John Warner Center for Green Chemistry Startups in Berlin is named in his honor. Through his scientific leadership and commitment to sustainability, Dr. Warner continues to redefine the future of chemistry for a safer and greener world. We are truly privileged to have him with us today. I now invite Dr. John C. Warner to deliver his keynote lecture. Sir, please.
Thank you very much. It's my honor to be part of this wonderful meeting, and I thank all the organizers, all the guests for inviting me to be here. It is a little bit after midnight in Boston in the United States, so it's very late here. So happy to be here with you. I'm going to share my slides. Are you able to see slides if I share them? So my slides are being shared at this point. Hopefully you can see them good. Yes. Okay. So thank you. I want to share some thoughts with you all today for the opportunities and the imperatives of working to solve these problems that we have in sustainability and the circular economy. Of course, there are many approaches to sustainability. There's responsible care, safe and sustainable by design, resilience, systems thinking, limits to growth, UN SDGs, circular economy, biomimicry, ecology of commerce, cradle to cradle, planetary boundaries. There's so many different approaches. All of these approaches are wonderful. All of these approaches are different, but we have a diverse set of problems that are facing our society, and we humans are very diverse, and so we need many different approaches. I get very sad when someone says, this is the correct approach, and this is not the correct approach, and this is tomorrow's approach, and this is yesterday's approach. We really need to work together and allow all of these approaches, because they're all different and they're all good. I have been working in the field of chemistry, material science, and sustainability for nearly 40 years. And when I go to sustainability conferences, even today in 2025, most people are still talking about why. They talk about, petroleum issues, plastics in the environment, climate change, toxics, and things like that. And then many people talk about what we should do. We should work on the UN SDGs. We should do LCAs. We should do this. And the urgency is important. And the metrics are important. But the most important thing, while why is important and what is important, most important is perhaps how. How are we going to solve these problems? So why and what describe the problem, but doesn't solve the problem. So I feel green chemistry is unique in that it focuses on the how. What do? We take natural resources and we extract molecules and ingredients. Then we take these molecules, and what does that mean? We mine materials, we take things from agriculture, we extract nitrogen from the air, we use fossil deposits, we use water. And then what do? We get these materials from nature, and then we do chemistry. We take simpler molecules, and we make more complicated molecules. For example, we take hematite, chromite, and coal, and we make stainless steel. We may take some agricultural products like molasses and starch and a fossil product like petroleum, we make a series of molecules that ultimately make something like perhaps an adhesive, a glue. Or maybe we do the same thing with sodium chloride and petroleum, and we make this complicated molecule, and then we combine it with another molecule, and we make a blue pigment. Or we maybe make a polymer like ABS. Now we've made all these molecules. We've extracted them from nature. We've then done synthetic transformations. Now we're going to put them together. We're going to make products. For example, we could take the polymer in the blue pigment and make blue polymers. Then we take these polymers and we injection mold and we form a part like this here. Then we combine that with the stainless steel. We cut out pieces of the stainless steel, and then we use our adhesive. We put everything together, and maybe we make a product as simple as a pair of scissors. Look at all the steps, all the chemical transformations just to make a simple pair of scissors. Now, I left a lot of steps out. It's very complicated how our society has evolved to make products. Now, what we want to do is we want to keep this product in use and reuse as long as possible. It would be wonderful if I continued to use my grandparents' scissors, and maybe my grandchildren go on and use my scissors, and the scissors last forever. But that would violate the laws of thermodynamics. It is inevitable. Because of entropy, something will go wrong. And eventually our products don't last forever, they break. Something happens. Now, what we want to do is we want to, as best as possible, mechanically recycle. We don't want to do any chemistry, you just want to disassemble and reassemble, so we have this assemble, disassemble loop. So for example, I might want to extract with a solvent the adhesive, maybe melt the polymer and melt the metal. Then take it and remake the adhesive, remake the plastic part, remake the metal part, put it together, and remake my scissors. Wouldn't that be wonderful? But here's the problem. Entropy again. Every time we mechanically recycle something, every time we melt the polymer, every time we grind a polymer, every time we try to mechanically recycle, we do a little chemistry. We break the fibers. We break the polymer because of entropy. So although I can talk about mechanically recycling a product, in 2025, we haven't invented technologies that allow us to do it. Maybe someone published a paper somewhere in a journal where they took 22 milligrams on a microscope slide for a lot of money. But at scale, in the world, we still don't know how to do this efficiently. It needs to be invented still. All right. So now we mechanically recycle as many things as possible. Now we have to do some reverse chemistry. We need to do the reverse chemistry. If you think about it, what happens with us humans in nature? We eat food. I don't know at what time. It's very early in the morning for you, I think, right now. It's very early in India. You had breakfast. When you ate breakfast and you ate the food for breakfast, you broke proteins into amino acids. You broke carbohydrates into sugars. You broke fats into fatty acids. But that's not all. Think of what happened in your body. As you broke those molecules in the same cells at the same time, you grew hair, you grew skin, you grew blood, you made energy. Nature doesn't separate the construction and deconstruction of molecules. Nature does them both at the same time in the same place. We humans haven't done of that. Think about it. In one building, there is a factory that makes molecules. And in another building, they recycle molecules. We never do them in the same place. So, for example, wouldn't it be amazing if we could take our glue, our adhesive, and reverse the chemistry and go back to the starting materials? In 2025, we don't know how. It would be great if we could take our pigment, our blue dye, reverse the chemistry. But in 2025, we don't know how. Wouldn't it be great if we could take our polymer and depolymerize and reverse that chemistry? But in chemistry, we haven't invented this yet. So it's one thing to want to recycle materials. It's another thing to be able to do it. We humans, we've spent all of our time learning how to make molecules. We haven't really thought of how to reverse that chemistry. Okay, so imagine we did. Imagine we have reversed as many materials as possible. Now, some of the materials we're not going to want to recycle. We're going to want them to degrade back into natural resources. And this is the regeneration cycle. So imagine if we took our polymers, our dyes, our adhesives, and we allowed them to convert back to water, carbon dioxide, and ammonia. Then we use that to grow more crops, more agricultural materials, and so that we could remake these materials. Right now, 90% of all the materials we humans use do not biodegrade. They're all petroleum materials that persist in the environment. We still haven't invented materials that can biodegrade. Only about 10% of the things we humans work with can. So it's not that we don't want to do it. We haven't invented how. And then finally, the whole point of this is to maintain stable ecosystems so that we don't hurt the environment. I just described a complicated transformation for one of the most simple products you could imagine, a pair of scissors. Imagine how difficult it would be for a solar panel, or an electronic circuit, or an automobile. We chemists, we material scientists, have a lot of work to do. And so this diagram that isn't one big circle, it's really a pendulum. And going clockwise is the human-built world. And going anti-clockwise is returning things back to natural resources. But everything doesn't go the whole loop. Some use and reuse, some assemble and disassemble, some do what I call the materials of metabolism, some degrade. We have to pick and choose and figure out. But we have to figure out how. And the other problem, of course, is we want to have the human-built world not impact the natural world. So that overlap on the bottom is a measure of sustainability. But every time we manufacture, every time we synthesize, every time we do extraction, things get into the environment. Emissions and leakage and waste happens, and we lose some sustainability. So what can we do? Well, the best way to address this is if we take the waste material, if we capture the emissions, and we use them as feedstocks. But in 2025, we haven't invented this yet. There's some examples, tiny little ones, but we have so much work to do. It's not that we don't want to, it's we don't know how. And so we need to invent technologies that help humans behave better. We need to reduce consumption. We humans use too many materials. But the technologies we have today will not really allow us to reduce consumption in a fair and equitable way. So we need to invent technologies to allow society to reduce consumption. And we have to invent technologies that are in harmony with nature so that if people do something wrong, if something gets into the environment, instead of it being a problem, it just degrades into natural resources. So everything has to be reinvented. This is why Paul Anastas and I, back many, many, many years ago, created the field of green chemistry, because it's not about wanting to do it, it's about learning how. Think about it. We need a science. When you learn chemistry, when you learn material science, do we teach people about mechanisms of toxicity? When we teach someone about making molecules and polymers, do we teach them about what makes something hurt the environment? Mostly we do not. So how can we ask people who are inventing the future to make things that aren't toxic, that don't hurt the environment, if it's not part of what we do when we invent chemistry? So we wanted not a philosophy, not a social movement, but a mechanistic science that has journals and textbooks and classes and conferences and workshops. And so that is the birth of green chemistry. Paul Anastas and I, we began doing this 1990, 1991. Our book came out in 1998. And what really frustrates me now in 2025 is still today, people will come to me and say, I'm very confused. What is green chemistry? I don't know. What is green chemistry? Well, this book has a chapter called What is Green Chemistry? In that chapter, there is a definition, the utilization of a set of principles that reduce or eliminate the use or generation of hazardous substances in the design, manufacture, and application of chemical products. And then we expand it to 12 principles. Okay? And so this is, if somebody wants to do circular economy, you use green chemistry to invent. If somebody wants to address some social inequity, you use green chemistry to invent something better. So green chemistry is not the why or the what, it is the how. And I have been so honored that this book has been translated in over 15 different languages. I have been myself to 93 countries, meeting kings and queens and prime ministers and presidents, but I'm just a name on a book. There are hundreds, thousands of people in the world, some of them in the room that you're at today, that are leading and becoming the people who are changing. I'm just a convenient, figurehead for the movement, but there are so many people. But here's the problem. If everyone woke up tomorrow, every person, every company, every brand, everybody said, we're going to do sustainability. We're just going to do it. I would argue only 10% have been invented. 90% of the technologies we haven't invented yet. So this isn't some battle of good and evil between industry and environment. It's a crisis of invention. There are some things that are emerging, but right now in 2025, more than 80% of the technologies haven't been invented yet. So why am I now at 1:45 a.m. in Boston on a call talking to everybody in this room? Because I hope people in this room want to dedicate themselves, their chemical intellect, into turning a traditional technology into a safe technology. Imagine an undergraduate student is pouring beakers and flasks in a lab. And because she gets it right, hundreds of thousands, maybe millions of people she will never meet are no longer exposed to a hazardous material because a chemist invented something better. What could be more important for us? So the biggest barrier to a sustainable future is not desire. It isn't laws and policies. It's not government agencies as much as it is we need to learn how to invent it. And this is a problem. We need to reinvent how we invent, right? And so it's hard, right? There are infinite molecules possible. Think about all the infinite molecules possible. And there are infinite products, many different products we could make. How do you connect infinite molecules with infinite products? I love the books Lord of the Rings. It's like crossing the land of Mordor. It's so difficult. But I'm going to tell you my secret. Although there are infinite molecules and there are infinite products, there's only a small number of mechanisms and properties. Think about it. Some things stick together. Some things are colored. Some things dissolve in water. Some things are stretchy. You start running out of mechanisms and properties after about 50 or 60. So although there are infinite molecules and infinite products, if we focus on the mechanisms, it changes everything. So that a product is defined by its properties. You don't need to be a scientist. It's just a quantifiable consequence of molecular material mechanisms. Color, flexibility, hardness, something like that. Still not a molecule. A material property is created by a material mechanism. That I define as an intermolecular process between more than one molecule. So it's like polymer crystallinity, Young's modulus, Hansen parameters. Still not a molecule. But a material mechanism is defined by molecular mechanisms. Those are unimolecular, intramolecular processes like bond rotation, van der Waals surface energy, hydrogen bond potential. Now we can go from molecule to product or from product to molecule using the logic of chemistry. And if you want to do sustainability, put it on the list. But if when you were a student, when you took courses, if you didn't learn what is the mechanism of cancer, what is the mechanism of biodegradation, what is the mechanism of all these problems in the world, how are you going to invent something that doesn't do something if you haven't learned the fundamental science behind it? And that's the point of green chemistry. Now, we can go between these verticals using good old-fashioned intuition, or we could use the new AI machine learning tools to go between this. And I could do this make the next Apple product. But here's the thing. We humans have been doing what we call modern chemistry for about 200 years. But nature has been doing chemistry for 3.8 billion years. We need humility. Instead of thinking we're going to do everything and we're going to make molecules do what we want, we need to have humility and look at nature. And instead of just looking at an Apple product, look at nature's Apple product and ask ourselves, how did nature make a water barrier? How did nature control viscosity? How did nature control transfer across membranes? If we, with humility, learn how nature has created all of its molecules and materials, now maybe we can start moving to a more sustainable future. So we got to worry about not only what a technology does, if we make a solar energy device, but we use toxic materials in depleting resources, is it truly sustainable? So we also have to worry about what the technology is. So and I've been doing this now since 2007. I created a company with a very small group of people and a very small amount of funding. And over the last 20 years, all we've been doing is inventing technologies. We've invented using the principles of green chemistry and this mechanistic theory. We've filed over 360 patents. We have invented technologies for over 40 companies. I never name a company that I work with unless they publicly say something. These companies have issued press releases. Oh, we worked with John, wanted to invent something. There's a whole bunch that I can't talk about, but we've invented. And we have created our own companies. So I've spun out 11 companies so far. We have a pharmaceutical company, we have a cosmetic company, a construction materials company, a solar energy company, and we've shown that using green chemistry not only has a moral and ethical basis, but it also accelerates the innovative process and goes from an academic publication to a product in the real world. And that, I think, is our crisis in sustainability. We are publishing more than 100 times the papers annually than we did 20 years ago. But they're not making it to the real world. They're not becoming solutions for society. And we need to figure out how to make this transition from the academic journal to the people that need these inventions. And so what wakes me up, what keeps me awake at night, what worries me, is we still have so much to do. Like I said, 85% of the technologies. So I talked about why, I talked about what, and I talked about how. But the most important thing is who. Who's going to do it? And that, I hope people listening to me right now in this room and online realize that this is not going to happen unless you do it. And so my hero in the world, the person who I believe is doing more for society than anyone else, happens to be my wife, Dr. Amy Cannon. She runs the nonprofit organization called Beyond Benign. And she helps colleges and universities find a way to change their curriculum to bring the principles of green chemistry into the required curriculum, not as an elective, but as something that defines what it means to be a chemist. It's called the Green Chemistry Commitment. And as of today, over 261 is the count today. 260 universities globally have signed this commitment. Now that's a big number, but it's still just a tiny bit. So people I'm talking to today, you're at universities, you are professors, you are administrators, you are students. I would love it if your university signed this commitment, because that's what's going to change the world. It's not enough to want to make sustainable technologies. I want to play the violin. Doesn't matter how much I want to play the violin. If I don't have a teacher that teaches me how and I don't practice, I'm never going to play the violin. So this isn't a crisis of desire. It's a crisis of ability. And if we keep teaching chemistry the way we taught chemistry 50 years ago, we're not going to solve these problems. We need to change the way we teach chemistry to include mechanisms of toxicity, mechanisms in the environment, all the social issues. And I believe in my heart, if we teach students and chemists how to do this, they will, and we will change the world. Thank you very much for including me in your conference today. It's a pleasure to be speaking with you, and I hope you have a wonderful conference today and tomorrow. Thank you very much.
Thank you, sir, for your extraordinary deliberation, especially on green chemistry. The institution and the department feels honored by your valuable presence with us in spite of it being an odd hour in the US. I now kindly request our head of the institution, our respected Dean ENT, to present a small token of appreciation and honor to the chief guest. Thank you, sir. In the words of James Allen, no duty is more urgent than that of returning thanks. I request Dr. T.V. Rajendran, Assistant Professor of Chemistry, to propose the vote of thanks.
Good morning to one and all present here. On behalf of the organizing committee, it is my honor and privilege to propose the vote of thanks at the conclusion of this inaugural section of this international conference. First of all, I would like to convey our sincere thanks to the management, director sir and dean sir, SRM IST, Ramapuram, for giving permission to conduct this program. First and foremost, I extend our heartfelt gratitude to our chief guest and guest of honors for your encouraging messages and for highlighting the importance of global collaboration in this field. I also express our deep appreciation to our keynote speakers who shared thought-provoking perspectives that will undoubtedly guide the discussions in the coming sections. I express my sincere thanks to our HOD ma'am, who always act as a backbone to our entire department activities. A special word of gratitude to our distinguished dignitaries, delegates and participants from across the world. Your presence enriches this conference and reflects the global significance of the themes we are addressing. We extend our appreciation to our partner institutions, sponsors, and collaborating organizations whose support has made this event possible. To the organizing committee, advisory board, and conference secretariat, thank you for your dedication, meticulous planning, and tireless efforts in bringing this conference to life. Our sincere thanks to the technical team, media team, and volunteers for ensuring that every arrangement today, from registration to audiovisual support, ran smoothly. So finally, to everyone attending this inaugural section, whether in person or virtually, thank you for your enthusiasm and engagement. So with that, we officially conclude the inaugural section. Thank you, and we look forward to our active involvement throughout the conference. Thank you, one and all.
Once again, and on behalf of the Department of Chemistry and the prestigious institution SRM IST Ramapuram, I take this humble opportunity to express our sincere and heartfelt gratitude to all who made the day a remarkable milestone to speak of the memories everlasting in the years to come. Thank you everyone and wish you all great days ahead. A small announcement, we request the participants to gather around outside the auditorium for a group photo. And I now request all of you to raise in your seats till the delegates leave. Thank you once again, everyone. I request all the participants to assemble outside the auditorium for a photo session followed by high tea, and be back here after 15 minutes for the most awaited plenary lecture session.
In addition to that, SAEST Golden Jubilee Young Scientist Award for the year 2015. He is also a top 2% of world scientists in the area of energy material as released by Stanford University from 2020 to till date. His research interest mainly includes electron transfer studies, electroanalytical chemistry, electrocatalysis, energy conservation and storage devices, and we welcome Dr. V. Ganesh sir to take the session. Thank you.
கேக்குதா? Yeah, okay. Thank you, Dr. Venkat, for your kind introduction, and thank you, Professor Prabhu sir, for chairing this session. Very good morning to all of you. Before I start my lecture, let me thank Professor Helen Kavita madam for providing me an opportunity to share with you guys what I work on for the past 20 years or so. It's been my pleasure to be a part of this wonderful conference, and let me start smile with a lot of stories so that I can make you guys smile. Okay, so today I'll be talking about sustainable electrochemical technologies for energy and environmental applications through molecular engineering of materials. Okay, so before I start, what do I do? I'll talk about where do I come from. Okay, then I will spend a little bit of time on why people are involved in doing research. Then I talk about the molecular engineering of materials, what we work on to develop in the area of biosensors, and from there I will try to correlate with the bioenergy aspect of it, and finally I will talk a little bit about energy. When I look at the schedule, I see that most of the talks are on batteries and environment related. So I will slightly change over, but I will teach you some fundamental electrochemistry so that you would be able to understand the later talks well. Okay. Now, okay. Slide mover is there in this slide mover. Okay. Oh, it's not. Okay, no issue. Slide mover orgama. Pointer is there. Illa adu connect aayirukku. Okay, slide mover is here in this. Illa connect aayirukku. Yes, pointer is working. Okay, so let it load, no issue. Let me talk about where do I come from. By the way, since don't worry about it. I will. My target audience is students. Okay, so it's like a lot of things you can learn if you are a first speaker. As you can see, how do you make up a man to give a talk? How do you connect a mic, etc. So it's a good advantage so that I can spend more time on what I want to communicate to you guys, right? So I came from a place called SICRI, Central Electrochemical Research Institute. I can tell you this is one of the constituent laboratories of CSIR, which is Council of Scientific and Industrial Research. We have roughly about 37 laboratories located across India. I can say that we have lab at North, IIM, IIM Jammu, Indian Institute of Integrative Medicine. We have lab at Jorgat, Northeast, that is called Northeast Institute of Science and Technology. We do have lab at Trivandrum, NIST Trivandrum, and we do have lab at West NCL, Pune, etc. Okay, I can tell you SICRI is one and only research institute in India completely devoted to the field of electrochemical science and technology. So you talk about anything related to electrochemistry, let it be starting from looking at fundamental aspect of electron transfer reactions that occur at electrode-electrolyte interface, to material design, to instrument and device fabrication, etc. for target application. We do a kind of multidisciplinary research approach, and apart from this, we do have good analytical facilities, right? And of course, our institute is about 8 decades old, and I can tell you SICRI has contributed many things, both towards the fundamental aspect of electrochemical science and technology to national development in general. Okay, so you may have to move the slide, sir, every time. Huh?
No problem, sir. I will.
Please take a chair, sir.
No
I'm
problem.
very sorry. Please take a chair and sit. No, bro. So, the institute was established in the year 1948 by then Prime Minister Sri Pandit Jawaharlal Nehru ji, and it was declared open in the year 53 by then President Sri Sarvapalli Radhakrishnan. Okay. So, during the inaugural function, Sir C.V. Raman was there. I'm sure most of you would know. And he posed that question. Just think about it. What are these laboratories going to do? Unless otherwise, the workers in this lab feel that it is up to them to do their very best. Otherwise, these laboratories will remain as a giant question mark in the sky. He was a physicist. He was looking at the sky. Look at the question he posed during the inauguration. He questioned even the existence of institute even. But I am sure if Raman would have been alive today, he would be more than happy to see what SICRI has contributed over the past 8 decades or so. Starting from providing corrosion prevention coating to Bamban Bridge, which connects the mainland Mandapam to the island Rameswaram. Continuing on that line, we have developed many ion selective electrodes like pH electrode, you guys would have heard about, chloride electrodes for specific detection of chloride, etc. And in this series, the recent addition being Make in India product of 100 unit cell fabrication of lithium ion facility that is established at our Chennai unit here in Chennai, right? So, of course, my aim today is not to talk about SICRI's achievement, but to tell you that what SICRI is all about. So, let me repeat my sentence again. Even now, SICRI is the one and only research institute in India completely devoted to the field of electrochemical science and technology. Okay? As far as I am concerned, basically I am a chemist. Electrochemistry is my bread and butter. I do take concepts from material science and biology to come up with essentially sensors and devices, mainly for energy and environmental applications and for biomedical applications. So, what am I going to do today? I will talk a little bit on electrochemistry, meaning why electron transfer reactions are important. Then I will talk about how do you engineer the material at molecular level so that you can impact the applications you would target on. Okay. Now, most of you guys would think about why people are involved in doing research, right? We had an excellent talk by, Professor Warner, and I feel really humbled, to talk after his lecture, and it was really thought-provoking, right? And I go back and look at why do you, basically involved in doing research, essentially to do R&D. This is the reason. These are the top 10 problems which we will face in the upcoming 50 years or so. Starting from energy, water, food, environment, poverty, terrorism, war, disease, education, population, democracy, etc. I can give examples that each of these is going to be an issue, right? Take for example energy, right? You do know, you all have a mobile phone with you guys, and we use mobile phone as what? A camera, as a computer, and you use mobile phone as a telephone, right? And these things happen because of science and technology. You follow me, right? And our Indian government is, brave enough to announce that by 2030, all the vehicles on Indian road would be of EV, electric vehicle, right? So how are we going to achieve that target? We need battery, associated electronics to drive vehicle. We need to incorporate AI ML model on this, right? That is going to be a big challenge. Now, since I predominantly work on biosensors, Let me give an example for disease, right? When I was a kid, my father used to take me to a single doctor, okay? And that doctor would give me an injection or a tonic if I get a fever, okay? And most of our guys would know, in 2 or 3 days, you feel okay and you take your bat, start playing cricket, etc. Okay. And now if you guys go to a doctor, let's say for stomach upset, what are the questions you guys have to face? By the way, sir, you are not allowed to see the doctor straight away. First one nurse will come and check you. Sir, would you just check your temperature? Can I check your pulse? And why don't we go and check your blood glucose level? Do anyone, by the way, it is not to criticize anyone, just to understand the science, okay? So just think about, do any of one ask, why do we have to do that? You went for a stomach upset, by the way. Did any one of us ask, are there any correlation between, let's say, temperature, pulse rate, sugar level with the stomach upset? We never ask. Something is not coming, please check here, right? We give our other hand. So think about it. And I'm here to ask mostly questions. To some questions I will provide answer, but I want you guys to think most of the time, okay? Now, and we also give disease to many names to disease, right? Starting from chikungunya, muttongunya we have not given it, right? Ebola, Nipah, AIDS, and the recent addition being COVID, right? So health is going to be a big challenge in the upcoming days. Okay, more than that, of course, Professor has already highlighted. In 2012, human population across the globe was estimated to be 6 billion, and it is expected to grow roughly twice by the year 2050. So how are we going to accommodate all those people in global earth, providing them, let's say, good drinking water, healthy food, greener environment, green energy, etc.? The only way is to do R&D, right? And more than that, when we make a little bit step towards achieving this goal, we will realize the dream of our Honorable Prime Minister Sri Narendra Modi ji, self-reliant India, right? Atmanirbhar Bharat. Don't ask me, are we not self-reliant earlier? That's up to you to think about, right? Next slide, please. Yeah. Now, keeping this in mind, I can tell you that electrochemistry can provide solutions to most of those global issues. And in order to do that, we need to understand what electrochemistry is all about. I know mostly electrochemistry is omitted subject in your undergrad and master's degree. Even when I was reading, I was interested mostly in inorganic. Okay. But I took physical chemistry for my PhD, and unfortunately electrochemistry, now I love electrochemistry. Correct. Let me ask a series of questions. You guys don't have to answer, just think about it. Then you will understand the importance of electrochemistry. We all have good food in the night, right? And we go to bed and sleep aramse, sleep comfortably. Who asked you to wake up in the morning, right? You may be disturbance from mobile phone, from your brother, sister, parents, etc. Let's say you wake up and you get ready in an hour or two, you feel hungry, right? Why do you feel hungry? Nobody asked you to feel hungry. And you have good food, let's say good healthy food. And when you catch a bus to come to university, when you look at someone, you feel happy. When you look at someone else, you feel very much irritated, right? You express your emotion. Why do all these things happen? Why do all these things happen? If you look at it in a broad way, all these things happen because of, let's say, biochemical reactions that occur in our body. I would go one step ahead and say that all these reactions occur because of biomolecules that undergo either oxidation or reduction process. The moment I talk about such kind of redox reaction, electrochemistry comes into picture. You follow me? So, electrochemistry in general deals with study of electron transfer reactions at interfaces. It could be solid liquid, it could be liquid gas, or it could be solid gas, etc. And in general, it deals with two different kinds of reaction. In one case where you derive an voltage based on inbuilt chemical reaction, Battery is a typical example. I'm sure most of the talks on lithium-ion battery and fuel cells, for example, batteries would talk elaborately on this. Just keep it in mind that voltage is generated because of inbuilt chemical reaction, inbuilt redox reaction associated with that material. And the second aspect is, you guys should have read in most of the newspaper that water could be used as a fuel to drive vehicle. Can we use water to drive vehicle? How many of you guys think yes? How about thermodynamics of that reaction? I know madam, since she work on it, she would know. None of you think, right? Similarly, like this, I was giving a talk in a college on a very lighter note. Then somebody said, yes, it is possible to drive vehicle. My father does, my uncle does, right? Then I switched over to English and asked, can we use water as a fuel to drive vehicle? Taniya oothi vandi ottalaman kekkalam. Purida. So, how about thermodynamics of that reaction? Delta G, water, undergoes splitting reaction to give you hydrogen and oxygen. Delta G of that reaction is positive, 237 kilocalories per mole. You guys know, when delta G is positive, the reaction is non-spontaneous, and if delta G is negative, the reaction is spontaneous. And fortunately, electrochemistry gives you clue, and electrochemistry gives an opportunity to tune delta G from non-spontaneous to spontaneous. How do I do that? This equation you guys should have heard about. Delta G is minus NFE, gives free energy. So for a given process, both N and F are constants, right? N is number of electrons, F is Faraday's constant. I hope you guys know what Faraday constant is, right? What's the value? I am looking at student, nobody is opening. 96,500 Coulomb. Is it correct value? How do we get that value? How do you define 1 farad? Charge of 1 mole of an electron. Okay, don't worry that I am telling lot of things, but learn. Okay, 1 farad is charge of 1 mole of electron, meaning you multiply charge of 1 electron, which is 1.602 into 10 power minus 19 coulomb, with Avogadro number, which is, I hope that you guys know, right? 6.023 into 10 power 23, right? So you multiply these two, you would get 96,484 point something coulomb per mole. That's the value of Faraday's constant, by the way. So for a given process, both N and F are constant. The only variable parameter is potential. So you apply a potential of 1.23 volt against the standard hydrogen electrode, you would split water into hydrogen and oxygen. In a typical electrolysis cell, water undergoes oxidation at anode, gives you oxygen, and at cathode, water undergoes a reduction to give you hydrogen. Meaning, you can generate voltage, you can drive chemical reaction by applying voltage. That's the second kind of reaction. Okay, so in general, electrochemistry is very, very powerful because of 4 reasons. The first one is delta G is minus NFE, so you can tune delta G between spontaneous and non-spontaneous reaction. And the second one, because of the electron transfer reactions that occur in a very confined space. What do I mean by that? The moment you dip any conducting electrode into an electrolyte, there is a spontaneous formation of electrical double layer at interface. That leads to a parameter called capacitance that is correlated with potential through an equation C is equal to Q by E. That's where the potential in electrochemistry originates from. Okay, now the typical thickness of this layer is of the order of nanometer. Okay, and you apply about, let's say, 100 millivolt within that nanometer, 6 volt per meter. Just think about, you apply just 100 millivolt, but it gives you 100 into 10 power 6, 100 million times volt per meter. And that's why many classical reactions that are not possible through chemical method, it is possible that you can perform using electrochemistry just because that reason. Okay. The third one is this one. you can correlate, you can press one time, yeah. You can correlate the electrode-electrolyte interface to different electrical circuit elements like uncompensated solution resistance, double layer capacitance and polarization resistance. Meaning you can quantitatively measure these parameters and these parameters are correlated directly with the kinetics of the reaction. You guys follow me? That is the third advantage of electrochemistry. The fourth advantage is you can basically look at the system at equilibrium, near to equilibrium and far away from equilibrium. Why do we worry about equilibrium? You guys know how do you define an equilibrium? How do you define an equilibrium? Chemists are there, right, in the audience? Equilibrium, everybody define manuva. I'll give you one clue. Rate of forward is exactly equal to rate of reverse reaction. What about the second point? Delta G? Yes, delta G is 0. So in case of electrochemistry, delta I is 0 and delta M is 0. Recall Faraday's laws of electrolysis, right? Unless otherwise, a system satisfies all these four conditions, you cannot term the system at equilibrium. Now, equilibrium is a state where electrode-electrolyte interface exhibits its real characteristics. Fortunately, in electrochemistry, we have techniques to measure the parameters at equilibrium, like potentiometry, for example, measurement of surface tension, measurement of capacitance, etc. And we can perturb the system by applying a small perturbation, right? Assume I am coming here to give a talk, but you guys don't know. While walking, suddenly I hit someone. Okay? Suddenly I hit a participant. How does the participant would react? Assume that he doesn't know I have come to give a talk, right? You guys follow me? What would be his immediate reaction if I just hit him? He will hit me back. If he is a very angry person, he may kill me back. That's a secondary thing, right? He will hit me back. That's what Le-Chatelier principle talks about. If you apply a stress or stimuli to the system at equilibrium, the equilibrium will shift in such a way that it will nullify the stress. And in electrochemistry, the origin of potential due to the formation of spontaneous double layer at interface is a kind of perturbation to the system at equilibrium. And the system responds to that perturbation, and that perturbation is nothing but your current. You follow me, right? So, we have fortunately techniques in electrochemistry. You can look at the system at equilibrium, near to equilibrium with minimal perturbation like impedance spectroscopy, shuffle, polarization, etc. And we can also apply a large perturbation, large disturbance to the system at equilibrium, and then also you can monitor how it is, behaving to the perturbation, like voltammetry techniques, cyclic voltammetry, linear sweep voltammetry, pulse voltammetry techniques, etc. So these are the four advantages through which electrochemistry can provide a lot of information and correlate with kinetics parameter, rate constant parameter, etc. Now, since I am going to talk a little bit on biosensors, what I work on, and I will correlate with bioenergy, it is important to understand the chem-bio interface, right? I am sure most of you guys would play games, right? And during the break, what do you guys take? When I asked that question, one college student said, we do take rest, sir. Yes, no, during the break, you guys take rest. Then I realized that is also important parameter. We do take normally glucose, right? Why do we take glucose? It gives very good instant energy. How about delta G of that reaction? Sir talked about photosynthesis in the morning, right? Glucose undergoes oxidation to give you 6CO2 plus 12H2O plus energy. Energy comes in terms of ATP conversion to ADP plus PI, right? Phosphate ion. And delta G of that reaction is negative 46.2, 47 kilocalories per mole. You follow me? So that's why we do take glucose. It is important to understand how the electron transfer reaction occurs across the membrane. How does it develop the membrane potential? so that you can manipulate the human behavior by applying a small voltage. Assume ECG electrode, no? We do record ECG, and you prick your brain with 2 electrodes, and you apply a small pulse, and you manipulate the human activity. My former director used to say, when students don't focus, just prick their brain with 2 electrodes, microelectrodes, apply a potential so that their brain will focus and study. That's where, he was talking about controlling neurotransmitters. You guys know about dopamine, L-dopa, serotonin, epinephrine, etc. That's, molecules are neurotransmitters. Okay. Now, so keeping that in mind, in our group, what do? We work on developing different electrode materials, and we modulate electron transfer across this interface through engineering materials, meaning we develop and synthesize molecule and material so that you can modulate electron transfer across the interface. For example, if I have a small aromatic unit, I can enhance the electron transfer, or if I have a long aliphatic chain, I can minimize, I can block the electron transfer reaction, etc. And we introduce different kind of nanomaterials essentially to play with enhancing sensitivity, kinetics, rate constant of the reaction, etc. Okay. Using this, we were monitoring many enzymatic reactions. Among the very fascinating structures, one more slide please. Yeah. We also worked on developing nano star-based structure. It is very simple to prepare. You mix surfactant with water. You do know, depends upon the concentration, you can, end up with having micelles, reverse micelles, liquid crystalline phase, and we used one among the liquid crystalline phase like a hexagonal liquid crystalline phase. Look at the structure, right? It is simply a Triton excentrate with water system. And when I play with concentration, I have a domain where aqueous region is limited, so that I can carry out the reaction only in the aqueous phase and control the growth of the resultant nanomaterial. You follow me? And this structure is fascinating because depends upon the length of the arm or sharpness of the arm, you would get many interesting characteristics in case of AZRS, surface enhanced Raman scattering, etc. Okay, but we used that system essentially to modulate electron transfer reaction. Okay, now, apart from this, we also used enzyme, for example, glucose oxidase, the redox moiety, FAD-FADH to flavin adenine dinucleotide, FAD-FADH to redox probe, essentially carry out the reduction of metal from metallic state to 0 state, like 2+ to 0 state, and we played with playing pH so that you can tune the fluorescence associated with this. For example, if I go to acidic pH, I get a rosy red fluorescent emission from that nanoparticle. And if I go to an alkaline pH, I get intense green fluorescence as a signal. And we use such kind of material to basically enhance the electron transfer reaction. Now, among the many sensors we developed, this is one of our favorite. This is called the lipopolysaccharide sensing. Let's say if somebody is met with an accident, okay, whether that person would survive or not, how do we know? We take them immediately to ICU, and this molecule would provide information about our immune response system. It is a potent immune response stimulant of our human body. This is called the lipopolysaccharides. Okay, so depends upon the concentration. Initially, it will lead to organ failure, and ultimately it leads to what is called a septic shock, cell poisoning of the body. But as a chemist, if I look at the structure, you see I have a long aliphatic chain, I have a sugar moiety, and I have different functional groups, so that I can target each of these moieties as a structural pattern and create receptor. I can monitor the binding using the charge-based interaction. You see, for example, the molecules I showed earlier, we used a hydrophobic interaction to anchor the molecule on top of the electrode surface, and we developed a receptor that binds specifically to the functional groups and we added a lectin, which is called a sugar binding protein. And these binding events you can monitor using charge-based redox probe, since this involved electrostatic interaction. Okay, so in a way we created a kind of complementary reduction-based receptor. Now, I'm not going to talk too much on bio, but this experience has given us that we developed a material, we can monitor enzymatic reaction, tune the kinetics, modulate electron transfer reaction, etc. And the other aspect we worked on is mimicking the biological species. For example, there are two ways. You can either mimic the structure or you can mimic the function. Okay, so here we work on mimicking the function. You can move a few slides. I will tell you. Okay, all these things, because of time limit, I am not going into detail of it. But I can tell you, mimicking the structure as such is very challenging. But it is easy to mimic the function of enzymes. And why? Because we do know horseradish peroxidase, for example, that will reduce oxygen to a 2-electron reduction process to peroxide. And if we use another enzyme called bilirubin oxidase, that will reduce completely oxygen to water, which is a very challenging process. Why? I'll talk about in the upcoming slides. Okay. So these informations on working on biosensors provided us an opportunity to create systems, sustainable electrochemical systems, through which I can generate energy out of waste. Okay. One such system we worked on is microbial fuel cell, where I'm sure most of you guys would have heard about fuel cell. What do I mean by fuel cell? You can use hydrogen oxygen fuel cell, for example, right? And you develop a catalytic material so that hydrogen could be oxidized at anode. And if you look at the power output, our old champion you guys have heard about, no? So that's like battery. So that's the difference between energy and power we do talk about. You can go ahead. So we do work on such kind of materials which can, the hybrid vehicle I talked about, right? When you start the engine, you need high power. That's where supercaps comes into picture. But when you start changing the gear and running a car, what you need is a minimum amount of energy required to drive the vehicle for a longer duration. That's energy density. Okay. But when someone comes in between and you apply a brake, what you need once again is high energy, meaning high power. So that's where supercaps again comes into picture. That is called a recuperation of energy. So we do work on such kind of system. You can move. These are some of the fundamental aspects through which you can analyze the typical capacity behavior and how does it vary with the system. You can skip this, okay. So we developed the materials and simple electrolysis using electrochemistry. We do play with the composition of electrolyte and potential we apply. We get a supernatant and a precipitate, where supernatants are fluorescent nanoparticles, quantum dots, etc. we can get. And the settled precipitates are carbon materials like graphene oxide, reduced graphene oxide, etc. So that could be used for supercaps application, and the top one could be used for bio imaging applications, etc. So using this, we developed many capacitor system, both for aqueous and non-aqueous electrolyte. You can skip. And in case of environment, we can also develop systems where you can selectively detect pesticide, etc. We have developed many such systems. So to conclude, I can tell you that recall the global issues what I showed earlier. Electrochemistry can provide solutions to most of those global issues. And when you take concepts both from material chemistry and biology, you can come up with a variety of systems so that you develop smart material and smart sensing system. What do you mean by that, right? You guys are listening to me from about 11:45 or so. And who is this guy? Ganesh from SICRI talks about electrochemistry, kinetics, thermodynamics, delta G, microbial fuel cell, sensor, enzymatic fuel cell, etc., then you got bored of it. Okay, so you lean on the chair. The chair understands that you are not interested, so that converts into sofa so that you guys can sleep comfortably. That is the smart material we talk about, right? Remember, at the same time it can prick you. What do I mean by that? Kundu siyachu gutra madri. It can prick you. The moment you all the way from Karaikudi came here to deliver a lecture and you are sleeping, it will prick and make you awake so that you will listen to me completely electrochemistry. You follow me? That's the kind of smart sensing system I talk about. But in order to do that, we need a multidisciplinary group effort. I may be good in chemistry, you may be good in biology, somebody else may be good in physics. Unless otherwise we do take concepts from different disciplines, it would be very difficult to provide sustainable and viable solutions to the global issues. So with that, I thank you guys for your patient listening, and I would be happy to answer any questions, queries you guys may have. Thank you very much. Any questions? You guys can ask me questions, anything related to electrochemistry also. Yeah, you want to know? No questions? Okay. Yeah, please.
In case of supercapacitors, current collectors, we are using nickel foam carbon, sir. In case of enzymatic and other, what will be using, sir?
So what I showed you as enzymatic fuel cell is simply two disposable electrodes, like a screen printed electrode, you know. So we don't have to use a separate current collector for those systems. We load very low amount of enzymes of the order of, let's say, microgram, and we optimize the loading within that area. We simply club two screen printed electrode with a membrane in between and connect them as a fuel cell. That's the advantage of using enzymatic fuel cell, where you don't need any current collector. I do know most of the time you guys use either copper, nickel, carbon based system at current collector. That depends on your electrolyte. It can give you a lot of other issues like corrosion, for example, and it may bend, it may undergo deformation, depends on potential cycling, etc. This would overcome that issues. That's the idea. Good.
Forward electrode. How it is possible? So it's need at least the LED need 3 volt.
Yes. Very good. Now, to drive a wall clock, we need 1.2 volt, which is sufficient enough. LED, what we showed for the red color, it doesn't need 3 volt. It could be done at 1.5 to 2 volt range, but of course, depends on the color. For example, if I want green or if I want white, then the voltage amount would be higher. What we do, we connect enzymatic fuel cells in series, like a stack. So each one gives 0.7. If I want 3 volt, I would connect 4, 5 in series. You follow me? But having said that, you need to optimize because the current value will come down drastically. So the power density also will come down. But for example, in case of wall clock, no, even digital clock, 10 microwatt is sufficient enough to drive wall clock. Okay. So we generate of the order of hundreds of milliwatt with this. So good question, because remember you guys, when I talk about this microbial fuel cell or enzymatic, I'm not going to generate power like our electricity, right? It will generate a very small voltage and very small power systems that is sufficient enough to do, let's say, small power requirement devices, pacemaker, powering up sensors, etc. You follow me? So that's the kind of system I talk about. Good. Thank you. Any other question? Anything in electrochemistry? Yes, please.
Microbial fuel cell sir. Bacteria use பண்ணனும் மென்ஷன் பண்ணிருக்கீங்க. அது வளர்றதுக்கு எப்படி இருந்தாலும் ஒரு நியூட்ரிஷன் சோர்ஸ் தேவை. இதுக்கு நம்ம என்ன மாதிரி சோர்ஸ்ல யூஸ் பண்ணலாம்?
ஓகே. உங்களுக்கு ஒரு சிம்பிளா சொல்றேன். உங்களுக்கு வீட்ல உங்க அம்மா நல்லா சமைக்கிறாங்க. அந்த உட்காருங்க தம்பி ஒன்றும் பிரச்சனை இல்லை. அந்த ஃபுட்டு உங்களுக்கு ஓகே ஐ எம் யூஸிங் லாட் ஆஃப் தமிழ் சடன்லி. ஓகே, யூ மதர் குக் குட் ஃபுட் பட் யூ டோன்ட் லைக், வாட் டு வி டூ? We ask our brother sister to eat, right? No, we simply throw it in dustbin. And if you look at dustbin, ஒரு 2 நாள் கழிச்சு பார்த்தீங்கன்னா அதில் நிறைய ஃபங்கை மைக்ரோப் வளர்ந்துருக்கும். அது எப்படி வளரும்? That uses carbohydrate and sugar which is present in our food. ஸோ த மெட்டபாலிக் ப்ராசஸுக்கு மைக்ரோபுக்கு தேவையான உணவு எதிலிருந்து வருதுன்னா தட் சுகர் அண்ட் கார்போஹைட்ரேட். தேட் யூ கேன் ஜெனரேட். நாட் ஓன்லி யூ நீட் டு ஆட் நியூட்ரியன்ஸ் ஃப்ரம் எக்ஸ்டர்னல் சோர்சஸ். ஃபார் எக்ஸாம்பிள், we normally add nitrogen compounds. We add even sugar externally to that. Instead of that, you use waste water, sugarcane industry, biscuit industry, food processing unit, etc. That waste water itself, அதிலிருந்து that will use them as a nutrient to grow and metabolize. புரியுதா நான் சொல்கிறேன்? அந்த வேஸ்ட் வாட்டர்லேயே இருக்கும் சுகர், கார்போஹைட்ரேட், எக்ஸெட்ரா. that is sufficient enough for microbe to grow on the electrode surface. ஒன்றுமே இல்லை, ஒரு பென்சில் இருக்குல்ல, அதை சீவிட்டு நடுவில் உள்ள கார்பன் அதை எடுத்து ஃப்ரூட் ஜூஸில் மட்டும் வைங்க. யூ மானிட்டர் த வோல்டேஜ் டிஃபரன்ஸ் ஃபார் டேஸ். By the way, you cannot measure potential of a single electrode, right? You need another electrode to measure. I am taking sad time as well. So you dip 2 pencil rods and measure the potential difference between the two. Okay? Then you will know. Fruit juice. கடையில் கொடுக்குறாங்க ஆரஞ்சு ஜூஸ், ஆப்பிள் ஜூஸ், ஆர் Tropicana, fruity, anything you take and allow. Let's see how it grows. Okay, good question. Any other question? Okay, if not, in the first slide I have my email address. You can find vganesh.sikri@csir.res.in. If you want to know anything related to electrochemistry, you can write me an email. Okay, good luck. Thank you guys.
I'm sure you have all enjoyed Dr. Ganesh's lecture. I'm sure there are many more questions which we can have during the luncheon hour because we are running short of time. So let us give a big round of applause to Dr. Ganesh for this very excellent lecture on electrochemistry. Thank you, sir. And on behalf of the organizers, I thank him for the lecture.
Sir, I request Dr. Prabhu sir to honor Dr. Ganesh sir with the memento and certificate.
Our next speaker is Dr. Venkateshwarlu, Scientific Officer, Midwest Advanced Materials and Energy Private Limited, Hyderabad. Topic of his talk is Smart Materials for High Performance and Sustainable Lithium-ion Batteries. Lithium-ion batteries are in the news. The Nobel Prize 2 years back went for lithium-ion batteries. So I am sure you are awaiting Dr. Venkateshwarlu's lecture. Dr. Venkateshwarlu.
Good afternoon to everyone. Thank you, Chairman, for your kind introduction. So, how many of you know there's a lithium-ion batteries? Are you using the lithium-ion batteries? Are you using the lithium-ion batteries or not? Huh? Yes or no? Because I don't know, I am not going to the basic science and other things because I am a industrialist. Though I got some couple of academic, I am not going to the academic institutions, though I have some issues with health issues also. Okay, so because once you enter into that, once you develop a one product, not that one publication or one kind of or invention, something new, if you develop, that happiness is much more. So that's what I feel, that is because I wanted to do my PhD on the lithium-ion batteries, but unfortunately those days, 90s, people scared about me, the lithium will fire you if you don't have the controlled environments and all this. For material preparation, you don't need any kind of controlled environments. Okay? So only that cell manufacturing, cell process, cell making, you need 100% controlled environment. It is a very sensitive to the moisture, very sensitive to the impurities, very sensitive to your process. It is impure, the impurities not even in the electrode process, and even the electrolyte also. That's why lithium is very sensitive, very reactive as well. Okay? So the smart materials I use, because nowadays you see the nano materials, nanoparticles, nano different kind of ribbon, nano ribbon. Even I have one paper and the nano flowers, nano ribbons, nano wires, nano. So many things are there. All are good, but you have to see that is whether during the cycling process it will be, the structure will be sustained or not. For yeah, please next slide, please. Yeah, just we can skip just next. These are the, I have not seen that is the sustainable development goals. There are 17 are there, but before that, this is when I was doing the postdoc, we have find out that these are the essential challenges we face, not only India and the global challenges: population, education, health, environmental, food grains, poverty, political crisis, and democracy, and also unmanned wars. Today we have seen that. Okay, so our focus is on energy. Without energy is very, very difficult to us. Without mobile, it is very, very difficult to live, right? So mobile is our part of life. So similarly, energy is very much needed. But what kind of energy you want it? Energy, you want to enjoy with the energy which is electricity is generated by coal power, coal-based thermal power plant, or you wanted a green energy, that is a renewable energy, or any other sources. So this is the energy transition and environment. Now we have reached to the pollution levels too high. Particularly, I also stayed 7 months in the Delhi NCR. Again, I got affected so much because there, that is even the Supreme Court judges, their wards and everyone, so many news comes up, but it's very, very difficult to control the pollutions. But it has to come from you. Every day I used to travel to the, that is what is that river is there, that's the NCR region. I wanted to do something, but all the IT, I used to stay in IT people, apartments and all, but nobody least bothered about the next, what is happening to next to us. Every time you have Narmada or Yamuna river is there, yeah. So something we have to do at least once in a Sunday or something. Actually, that is my interest. I wanted to take students, even I want to have at my hands. So I want to do something, but some small lakes in the villages and all. But anyway, now I cannot do that. So these are the things you can see the pollution with diesel and petrol. And if you look at the electric vehicles, so there is no emissions at all. But emissions is there when you are producing, when your materials, raw material side, but not at the end. So this is why people are preferring the electric vehicle, because many vehicles, if you see the school buses, college buses, and the autos, rickshaws, everything is in the urban areas or the cities. So it is significantly affects our children's health. That's why, though it is on a mining side, there is a huge emissions of carbon dioxide, but in the city side, we are very comfortable zone. So morning also that our leaders have mentioned that you see the continuously increasing the CO2 emissions, and only that during the COVID time, it was slightly lower than. It may be the industrial, see that the industrial revolution, this electric vehicle revolution, these are all the things are required. If those things are not there, we will not find any jobs. That's why we have to go balancedly. When you are selecting a material, whether this material have environmental impact or the health impact or any other hazards. So these things, to be honestly, when I was doing a PhD, I don't know anything. I just blindly select the materials and take. But today that is not the scenario. So you have a good tools are available in your hand. You can find out from Google search or even the artificial intelligence is there or any other programs is available. You see that whether this material is good or bad. That is one simple example I want to give. If you want, your parents want to buy a house or buy a car or something, how many times you go and just inquire that? Similarly, here also, when you are selecting a problem for the even the master project or the PhD project, just select the best one. Even the UGC today, they are not bothered about the research publication per PhD. And the government of India is giving enormous incentives for the youngsters. If your idea you can protect, IP can be protected, and you can start, you can have an incubation center, you can start your startup, so your idea can be protected. Okay? So so many. That's the only thing is you just spend half an hour or 1 hour for the environmental or health purpose. So you can see that is energy security is important for us because overnight we cannot go achieve the net zero. So environmental protection, both are important for us. These are some of the electric vehicles emissions, and only the France is very low because they are using the nuclear power. Nuclear power also comes under the green energy. Other things you can see the electric vehicles 90 grams, 40, 50 grams, 20 grams, and 2 degree centigrade, that is 5 to 10 grams in future. That is for 2040 kind of thing. So another thing is population. We know that the population for India and China, but still we are a discipline, definitely will come out. We have the enough resources, we have the talent, and our ancestors or people have written excellent reports, but unfortunately we are not going through that. So when I was just looking for the I recently joined in this company, they are looking for the rare earth magnets. I was thinking that this is something new. 1958, there is an excellent paper with excellent diagrams. The 2 days back I found that. So 2 pages. But today rare earth metals are more than platinum and gold. I'm fortunate that this company, we are the first to set up the plants from the ore to the end product. Yeah, batteries, you all know that. So these are some of the vehicles. You have a various type of vehicles. That is a mild hybrid. You might have seen the Scorpio and all hybrid. Even the Toyota recently they launched a hybrid. So hybrid is hybrid cars, mild hybrid, micro hybrid, all these things. It will be 2 to 5 kilometers because initially only emissions are more. After the continuously running, emissions are less. And plug-in hybrids, that is the onboard charging will be there, and also it will go up to 30 kilometers with the DC, the battery power. And most of the things only the leader is lithium-ion battery. Lead-acid battery, we cannot use the lead-acid battery. The reason is it is heavy. Charging takes 10 to 15 hours. And the energy density is, it is 30 watt-hour per kg. Whereas the lithium-ion battery, if you go minimum 160 to 190 for a lithium iron phosphate cathode base, and NMC it is a 250 up to. So you can see these are some of the batteries which all are having each battery has unique features, and you have to select the battery as per your application requirement. All batteries are good. Today that lot of research is going on the zinc ion battery. You might have seen that zinc carbide is a thing that is a primary battery in our cordless things we are using. That is a so zinc ion battery. Now the already this Godrej has set up a pilot scale facilities in Mumbai. Godrej first they have got the technology from USA, and the zinc, and of course some of the companies also they are having the facilities. They are developing that zinc ion battery. The advantage zinc ion batteries is alkaline solution, KOH solution used as electrolyte. It is high safe, but only thing is any metal has tended to formation of dendrites. Whether it is a lithium or it is a zinc, any metal. So we need to have some kind of smart treatment or surface engineering is required. So that we need to find out. And that is even if you just coat the material with the thickness is very, very important. That's why ALD process is good for that 1 to 2 nanometer. You can just coat the material so that even the lithium ion battery, that surfaces cannot be attacked by your electrolyte species. This I put because that is you can see the theoretical values. That is 160 for lead acid battery, but you get only maximum is 50. At 70 you will get it for the bipolar batteries. So that you will be 30% lead will be reduced. That's why whatever per kg, if you reduce it, your energy density will be higher. Other things also, these things now lithium ion battery, we are close to the theoretical values. So you can see that significant improvement. When I was this technology was started in 1990 by Professor John Goodenough. Okay, it was 1300 milliampere hour of 18650, that which we are using for the laptops. Okay, earlier, not the people are not using the laptops nowadays because they use the polymers and pouch cells and all. So today that one is a 3200 milliAh. Same 18650 size. You see that is the evolution how it has happened. That's 1300 milliAh to 1500, 1800 to 2100, 22, 26, 28, 32. Even that France people recently they reported 4000. But see the problem is that the academic side. I am also very much interested. Academic, I used to collaborate with several universities. All IITs I used to collaborated during my industry. That's the battery research time. Even the Amar Raja, I have given us huge money for this. We set up a lithium ion lab in the SRM University, AP. Okay, that is we wanted to develop additive manufacturing. There will not be any solvent. For that, we have set up a lab. And unfortunately, the person who did PhD on additive manufacturing, he got a government job left. That's why it's a little bit lacking. So that's why you have to see all the parameters. Okay. So any diabetic fellow or any the bypass surgery person is taking some tablets, means it is going to affect on other organs or not. You have to see. So continuously taking all these things, what is your other organs is affecting or not. You have to check it. Similarly, once you get the capacity, I got this much capacity, immediately there is a big news in the newspapers. But what about the specific energy, power density, charging time, cycle life, cost per unit? India is running only cost per unit today. So there is no lithium ion cell manufacturers in India except Nash. They have did some 600 megawatt hour Nash energy in Bangalore, and Exide is coming up. Of course, even PLI scheme, Reliance and Ola, some extent. But the reason is, as long as you are getting a cheap product from there, so here you cannot sell it. That raw material, we are lagging the raw material, and raw material cost, process cost, everything if you do, it is almost 1.2 times of the Chinese. So that's why you can see lithium metal is unsafe. Why? Because of the, but today, I don't know whether I put the picture or not. I remove. Yeah, this here is there. Lithium is unsafe. You see this lithium battery 1996, I remember, I don't know the exactly. Moli Energy was doing with the lithium metal used as an anode. And the metal, as I mentioned, as the metal tends to form as a dendrites. And he was doing a Japan project, and there was a internal short circuit, and all the 1 lakh cells they are scrapped. So the same lithium metal today we are using for the again lithium ion batteries. This is the solid state battery. People are using lithium metal as an anode. Because lithium metal is 3.8 H per gram. Silica also 4.8, 4.3 or something H per gram. So the substitution, suddenly that is the Japan person, that is Akira Yoshino, what he was collected the cathode material from good enough and he was doing the polymers. He just integrated battery and he was successful with graphite anode. He suddenly replaced that lithium anode with graphite. Because graphite interplanar distance radius, which is interplanar similar to that of the lithium ionic radius. So that's why easily it will intercalated and deintercalated. That is that's why you call it a shuttling effect, rocking chair kind of. There are so many names are there: intercalation, deintercalation, insertion, deinsertion, like that people used to talk. So that's why. But today we are trying to do that is some modification of the lithium metal. It's not, we are not going to use as such. So that's why it will be energy density will be very high. People are using for the solid state batteries, which is a very thin battery. You can say. I will go to, I don't know what are the things are there. Yeah, these are the lead acid battery because I love the, though I was fond of this lithium ion, but when I joined in Amar Raja batteries, so I don't have option. I had to work for lead acid also. When I was working in lead acid, I got so much interest, so much to improve in this battery. Because people are not using the carbon as a additive in the one of the electrodes. But today the carbon is essential for that. So that's why even myself I did the carbon, different carbons. And of course earlier there's a foam carbons and other things are there. And you have a negative plate half of the lead based and half of the carbon based. So this kind of different combination, but the significant improvement is charge acceptance. So you can charge with a carbon, lead carbon chemistry based battery in less than 5 hours. Earlier it used to take minimum 8 to 12 hours. That's why the electric vehicle people are not preferring this one. But it is a safe. So these are materials, you can see that the top, that is 3 to 4, it is a cathode materials, and the bottom is the anode materials. And these are the different cathode materials are there. That is Professor John Goodall, that is a lithium cobalt oxide was the first cathode materials developed. And before that there is another cathode material was developed by Professor Whittingham, but that the voltage was 2.7, this is a 3.7. That's the difference. That's why people are more adopted in the lithium ion base. And cobalt is a very expensive, costly. That's why substitutions, nickel substitution, manganese substitution, and different kinds of chromium. There are lakhs of papers are there in the different combinations of that. And LTO, that is a lithium titanium oxide, is an anode. So graphite is good, but the safety wise, this is 10 times better than the graphite based batteries. That's why, but it's very expensive. And NCA, that was a Tesla is using NCA. They got the technology from SAPT. So even till today they are using the NCA materials. And very recently, that is a plant was set up in China. The China vehicles only they are using LFP. LMO is good chemistry, but unfortunately there has its own challenges. Limited cycle life because of the structural distortion, John Teller distortion, you can say that is, and a manganese dissolution at the high temperature. There are some issues, that's why it's limited the cycle life. And LFP, lithium iron phosphate, this is the cathode material good enough was developed with Indian author. So that time it was a 3.2, though nobody bothers about that. So today this is the hot cathode chemistry for all BES applications, battery energy storage, which is integrated with the solar and grid. People are using only LFP cells for the best battery energy storage systems. Of course, NMC is a moderate because you want to reduce the cobalt, manganese is introduced, and nickel also they introduced. Nickel now its percentage is gone to 90%. Another 5% is manganese and 80% is nickel, and 5% is manganese, 5% is cobalt, and another 5% is 3 to 5% is PVDF and carbon additives, rest of that. So because you need to have both ionic and electrical conductor, that's why we used to you add the carbon materials in cathode also. So these are the different form factors. So as I mentioned earlier, we use the 18650 for the mobile laptops. Now people change it to the pouch cells. So it is very compact and you can have more energy. So that is the first cell is cylindrical cell 18650. Now it is the 2170 size is increased, and also Tesla is recently announced 4280. And this is a prismatic cells. Prismatic cells, today the battery energy storage container level, they are using a 314 ampere hour single cell. That means 3.2 volts and 314 ampere hour. That they are giving to the India. Now China is upgraded to the 500 to 720 ampere hour of single cell. So that means in the same container, 20-foot container, instead of accommodating 5 megawatt hour, they are accommodating 6.7 to 8 megawatt hour. So that means you are almost 50% you are reducing the CO2 also. So these are of course demand for the lithium ions. For the terawatt level you need for the 1940s. And this is actually a complete supply chain. That is upstream, that is mining, and down midstream, that is the electrode process, and downstream your applications. So that's why this mining side, if you take, this is not a good chemistry. You need to have a energy as well as water, and it is toxic. But still in the cities and all, this electric vehicle people prefer because of children's health. And of course, 35 you need this much of materials because the ACC, Advanced Cell Chemistry, PLI scheme, government has given some 18,000 crores as incentives for that. So it's huge materials were required. Sorry. So you can see that is this is our battery resources in India. We do not have any other material except manganese and graphite some extent. India, you can see that 1, 2, 3, 4. This is a second basket. You can see that in India. But we need that is a gigawatt hour 3,500 by 2030. This is 40. You can say that 2030 we are only 160 gigawatt hour required. Of course, this is only, these are the different chemistries I put here. You can choose the chemistry of your interest as per your applications. So the chemistry, we see the energy, specific power, safety and performance, life, and also cost. Both cost and safety are more important for anything, any chemistry. So see, here is just, I done some checking that when 1990, what is the capacity? As I mentioned, 1,300. Today is 3,600, 2025. The same size of 18650. That means 18 mm dia and 65 length. And you can see that if we are increasing the capacity and it is automatically CO2 also. That's why here innovation comes. Either the material side improvement. So here we are very limited material we are using and getting the high capacity performance. Of course, in Gigafactory, if you see that is a coal 1 kg per 1 kilowatt hour, right? So here also gigawatt also a huge CO2 will be emitted. But you have to see that what kind of process you are going to adopt for the making the cells. Whether you are going for NMP PVDF as a binder or SBRS CMC as another aqueous binder, or you are going for a dry process without any solvents. You see the dry process, now it is a very hot topic and people are developing this process and it is only the 5 to 15 kgs per kilowatt hour. So already okay, sorry, I'll just wind up within 5 minutes, okay? You can ask. So these are all my papers. I don't want to go this one. So these are all extensively I did in all my in situ papers using X-ray absorption spectroscopy and X-ray in situ XRD in Taiwan. So yeah, these are the models we do that. Even you can see that cells we couple series parallel combination as per your application. This is for e-rickshaw and all. There is a lot of benefits for us. And this is a pack level. This is see I am maybe the first person who got this 180 ampere hour cell from USA. Getting this cell is I find very difficult, and 1 year I struggled. Finally, Amar Raja having a green that is Amar Raja food, so they have a green channel. So through them I got these cells and tested in 2012. So this is a separator. Chemistry people may be interested. So separator also is very, very important. You see that is when the Munot Energy, we started a company next to the Amar Raja, the Renugutta. So we have just 56 cells, cell phone batteries we cut open analysis we did, and separators we did. And these all the separators, whether 2 layers or 3 layers, PP or PPE, because PPPE, if you combine it, so during the abuse operations, what happens, one separator will be, the pores will be blocked, it is melted and blocked, so the ion transport will not be there, your battery is safe. So you can see that is a kind of lithium titanium and iron phosphate we use the safe and all. People are using for single crystal, polycrystal have some issues. That's why the cracks are developed in polycrystals. And now NMC 822 means 622 means 60% NMC, 20% nickel, and 20% manganese, 20% cobalt. Now it is 80% plus. You can see you can extend the range, battery performance and range. So this is I prepared for the recycling purpose. So this one person has used that lithium as an anode for even the conventional laboratory cells, and he reported huge, almost 5 to 600, I think so, watt hour per kg. So there are other chemistries are there, very interesting chemistries. Aluminum ion chemistries are there. Aluminum, Nalco is ready to give the funds if you are interested to develop aluminum ion battery. So there are the magnesium ion batteries are there. And of course zinc ion, as I mentioned already, zinc ion already people are working and there are other chemistries also, you can check it out. Lithium oxygen, that is lithium air batteries. Cycle life is important. You can see the lithium, sodium, potassium, calcium, magnesium, all aluminum. So this extensive research is going on the potassium also, calcium, magnesium is already known, magnesium, aluminum. Of course, these are the summary, you can see that's yes. So ultimately, how to use the solar energy 24/7. What are the tools you have? How to tap the solar, intelligent way tapping the solar energy. So that is very, very important. these batteries are getting important because you need to store the solar energy in the daytime and use this one in the peak hour time. So that is why the batteries are now become a very, very important. Yeah, thank you very much. If you have any question, please feel free, and you have my email ID is there. Anytime you can call me at up to 10 o'clock. Yeah, no problem. Because we used to review even 12 o'clock also sometimes. That's why some issues are coming. It's very, very tough time, because I contacted all the, when lead acid battery terminals got black spots are there, even the new samples. Whether we don't know whether it's due to corrosion, due to sulfation effect or something else, but we struggled a lot. That's why Amara Raja today, they have an excellent R&D facility. All our samples are, professors are taken and kept in the cupboards, so there nobody is analyzed, and we are to answerable to the customer. That's why Amara, and at the same time government also has given us some incentives, tax incentives. So that's why Amara Raja now they are having every facility, XRD, STM, particle size analyzer, impedance, everything. So that's why now they are, when I was there in the Amara Raja, just one doctorate for the lead acid, myself is a lithium ion, but today they have 40 doctorates. Each component they have one doctorate. Okay, thank you for your attention. So I don't want to take much time. If you have any doubts, please write to me. I will respond in 1 or 2 days, no problem. And it's very interesting topics. You have enough things you can do, that is the battery side. Not necessarily these batteries, graphene batteries. If you are someone is doing some graphite research and other thing, I told you graphene oxide. Graphene oxide is today, that is the limiting factor for the lithium sulfur battery. Sulfur is very $1 per kg, and is easily available in India. So nobody is addressing that one. Our Professor Mantiram is there, Armuga Mantiram, Texas University. He is working. Okay. So that's why there are other technologies which is unaddressable. So today even a magnet, it was the oldest topic, oldest material. But today it is become a gold. Okay. So enough opportunities are there. We can do better. So but only thing is teamwork, discipline, and timeline. These are the three things you need to maintain or follow, adapt. So there, you can anytime any doubt is there, I'll be available for, because I also worked in Ishwar Engineering College for 5 years. After that only I got a postdoc in Taiwan, so I moved out. I am the first person to get the research project in Ishwar Engineering College. Thank you for your attention.
Thank you, Dr. Venkatesh Wadlu, for your very exciting lecture on a very hot topic, lithium-ion batteries. If you are having any questions or queries, Professor Venkatesh Wadlu is there during the luncheon session. Please be free to ask him. On behalf of the organizers, it's my duty and pleasure to thank Dr. Venkatesh Wadlu for his wonderful talk. And on behalf of the organizers, we will present a memento to him.
Participants, lunch arranged outside the auditorium, and exactly by 2 o'clock everyone kindly assemble here. We need to complete the program. Okay. Thank you.
Yeah, everyone should assemble sharply at 2 o'clock, same place. After that lunch, so most awaited plenary lecture by Dr. Ranjini Arumugam ma'am and Dr. Brajesh Parekh sir and Dr. Gurunath. So after that, parallelly, physical oral presentation.
We are starting our afternoon session. It's my privilege to introduce Dr. Sivaranjani Arumugam, accomplished research scientist in biophysical chemistry, renowned for her contribution to quantum sensing, nanotechnology, and recent spectroscopic technique. Dr. Ranjani's work spans single molecule spectroscopy, non-linear optics, and innovative imaging technologies with numerous publications in top-tier international journals. She currently serves as a Director of Administration at SEED GmbH in Leipzig, Germany, where she oversees the production of quantum processors using diamond-based technologies, an emerged frontier in quantum applications. She has also served as a senior scientist at Leipzig University and previously as a staff scientist at Max Planck Institute of Multidisciplinary Science in Göttingen, where she pioneered research on diamond-based imaging and mentored postgraduate researchers. Her international experience includes roles as a research fellow at Savannah State University, research associate at Jackson State University, and postdoctoral scholar at the Pennsylvania State University, where she investigated DNA replication and repair using advanced spectroscopic methods. Dr. Ranjani earned her PhD in biophysical chemistry from the Indian Institute of Science, Bangalore, following top-ranked performance in her MSc and BSc studies in India. Beyond her scientific accomplishment, she is recognized for her leadership, mentorship, and commitment to public science communication, making her an inspiring figure in modern chemical and quantum research. I welcome Dr. Sivaranjani ma'am to take the session.
Thank you. Can you hear me?
Yes, ma'am.
Thank you for the kind introduction and the please share my screen. Is this visible? Let me go to the. Shall we get started? Shall we get started? Can we start? I can't hear you.
Yes, ma'am, you can start.
Sure. Sure, I'll get started. Good morning, everyone, and sorry, good afternoon, everyone in India. And it's a pleasure to be here in this beautiful conference to talk about our NV Center Diamond. And today I'll I outline my talk to tell you about how the quantum sensors are taking the sensor world. And our research focuses on nitrogen vacancy center in diamond. So I will tell brief things about how a nitrogen vacancy diamond the use of a quantum sensor and also quantum computing application. And finally, I'll conclude with my So here you see a beautiful picture of this is our physical world, Earth, and all the sparkling ones are the connected digital. So this we call it a digital world, and this is a physical world. And these two are nowadays so interconnected. So we connected with the Internet of Things. So what are these sparkling dots? This basically we call it as all most of them are made with the backbone is made up of its sensors, and sensors become the heart of any measurement system nowadays. and it is ubiquitous and everywhere. So we don't need to go into deep into how what are sensors and what are the applications are. It is there from our simple body thermometer, temperature measurement to advanced complex instrumentation, sensors everywhere. So why we choose about quantum materials and why they matter? So they are always existing, but we call it as a new state. So it is becoming it a transformating technological advancement in terms of energy efficient technologies. So it is governed by quantum effects at usable scale, example like topological two-dimensional strongly correlated systems. And it is also very useful in low power electronics and interconnects in terms of charge and spin transfer. And it exhibits novel functionalities, something like superconductivity, giant magnetoresistance, tunable band gap. So these are some of the main features of these uh, quantum materials, which are making them many more applications. For example, it becomes a foundation for the next generation of devices like quantum computers, low power memory devices, photonics, ultra plus logic devices. So not only technology, it is also a better way to do how we look into catalysts and highlight power systems and how we make use of this efficient energy storage system. So it's both affecting science and technology, and particularly in the application. So if you move on to quantum sensor, when you make sensors with quantum materials, it is one of the cutting edge technology, and it has many key advantages of conventional sensors. So how does the quantum sensor work? They make use of the extremely sensitive uh, to disturbances. So this means they potentially become extraordinary sensitive measuring instruments. So their sensitivity is extremely sensitive compared to the conventional sensors. Not only improves sensitivity, it cancels platform noise, and it becomes a relaxed hardware recommend for various applications. So not only they are a new class of sensor with a disruptive technology, and it has a very good range and robustness. And their main advantage is more towards perfection. I would not say 100% perfection, but more towards perfection compared to the classical sensor. So when we make use of this quantum sensor, we are looking into something very high sensitive at a low energy. So this is gain for us in terms of many sustainable features. So we can measure the coherence entanglement world with minimal power. So we can make use of exploit quantum states, like can we center cooled atoms or superconducting circuits for extreme precision. And we can make use to detect tiny signal either at room temperature or cryogenic temperature. Some of them are the properties. If you look into the application, like can replace GPS without more precise navigation and medical imaging in fMRI, MRI, NEC, and then infrastructure strain, etc. If you take into in the energy sector, we can make use to monitor batteries, grids, turbines, pipelines, how to reduce losses and prevent failures. So all these are, where it goes to the environment events so that we can make use of compact sensors for pollutants, seismic activity, climate variance. These are only few examples I could think of where I can put it, where you can use the quantum sensor for high sensitivity and low energy and sustainable measures. So few of the quantum sensing materials, so you're all expert in material science experts are here. So I have listed like 5 different major classes. One of them is atom and ion sensors, using strontium, yttrium, magnesium, beryllium. Some of them are. They are basically a range of trapped ion sensors. And the second class is the rare earth ion drop solids. Example will be lanthanide ion of the orbital. We can make use of like a YAG, doped YAG, and still like for making the quantum sensors. And third one is very familiar and quantum Nobel Prize in quantum dots with transfer material, chalcogenides, 2D materials with hexagonal boron nitride, so on and so forth, a colloidal quantum dot. And fourth class is perovskite, and it can be metallic aids with a formula AbO3. and which has unfilled d orbitals, which can be influence the behavior of the surrounding electrons, and these can be used as a quantum sensing material. And fifth one is, which is the carbon-based material. We know diamond is allotrope of carbon, and where carbon exists in a graphite or like a ball, like a Buckminster fullerene, and all three forms allotropes are well known for carbon. And one of them is diamond, and today my focus will be mostly on the diamond-based material. So in the diamond, are we looking into anything special? Yes, we make use of special type of diamond. We take the normal lab synthesized sparkling diamond, and we modify into what we call it as diamond NV centers in diamond. It's a defect in the diamond. We purposely create for research purposes. So moving on to nitrogen vacancy center in diamond, they are nothing but defects in the with the electron that can be manipulated by light and microwaves. For example, if you take into the cell of the diamond, the black dots are the carbon. So what we do is we purposely knock out one of the carbon and replace it with nitrogen. And we also purposely knock out the adjacent carbon, make it as a vacant. So this is nitrogen vacancy center. So this is balanced by the lone pair of electrons by nitrogen. So everything is intact. So this protocol has been studied over a decade, and then it's been well established how we make the NV center, how we create it from a normal diamond lattice. So this, once we have the NV center, you can see how we are talking about very much in atomic kind of scale. We are looking into now more into the from molecular frame to the atomic frame. So when we impinge with laser light, say 532 nanometer green light, they take up the light and they emit in red. And this emit colored photons at 624 nanometer. They carry the quantum information about the surroundings, both magnetic and the electricity. So this information we make use this fluorescence, what we get from the NV pair. We make use of for various many applications. So what are the advantages using NV diamond technology for sensing or computing? One of them, the major advantage is energy efficient and green. It operates at room temperature, so you don't need to use expensive cryogenic cooling or etc. And it needs just regular for 220 watts or 110 watts. So it's ultra low power optical and microwave control for everything for experiments. So as I said, there's no helium consumption and long material life, and it is non-toxic, durable, non-photobleachable, and it can be used endless cycles. And it has a very efficient when you impinge with a green light, and it uses perfectly the fluorescence, and it has a very efficient light matter interaction, and also it has an energy efficient edge field deployment. And it has significantly reduced the lower carbon footprint compared to the other materials. So this is one of the major advantages using the nitrogen vacancy based diamond technology. So how it is a quantum sensor? As I said, when we impinge with 532 nanometer, it takes up the light and reduces and emits fluorescence in the red at 624 to 638 nanometers. And this is it's atomic emitter, and it is a nanometer size, highly photostable because it's trapped inside the beautiful diamond lattice, so electrons do not escape. And there is a fundamental property, and there's a spin interaction with carbon with nitrogen, and also the lone pair of electrons, and that's beautiful. So we can study things in electron volt scale. And how do you produce it? You can either produce it in bulk or demand in or nano in scale with nanometer precision. So this protocol has been well established. So take into, we call it as a NVD as a dual sensor. One of them is the optical sensor. When we shine the green light, then it with the red fluorescence. So this imaging can be used for many purposes. For instance, one of them because it is less cytotoxic and almost no cytotoxicity itself. So it is used as a very good fluorescent biomarkers to study very many in vivo studies, live real imaging. And it also very good to detect electric fields locally, so it's been used, and super resolution imaging can be used. And then the spin from the system is used for the quantum information and the quantum meteorology science. So if you take it as I call it as a magnetic field sensor, this is a schematic of various magnetic field sensing materials. You are familiar with Paul, GMR, AMR, and this is where the around 1 microtesla, this is where the earth's magnetic field is, and squid induction coil. And the red one marked here is the NV center, NV sensor at room temperature. But if you think you're all expert working in these kind of fields, where you think most of the squid, hall, EMR, most of them are work in the low temperature. So you have to go into from 0 degrees and down all the way to the cryogenic temperature. So it is not like simple device you keep it in the room temperature and work on. But when you compare the NV sensor, they have a range in which pretty optimal range in which the working conditions can be done at room temperature. So they have a very good sensitivity, linearity, and range and frequency bandwidth and dimension. So the value we measure here using NV sensor is compared to somewhere between 1 microtesla to sub nanotesla. So it has a good range in which you can access a magnetic field sensor. So moving on to the application. So having said about the properties and qualities of the NV sensor, it is used in the synchronic devices experiment and application, quantum devices, cellular imaging, as this is less cytotoxicity, and also biosensor imaging, spin-based biosensor imaging, protein structure analysis. So these are not limited to these applications. These are the few major applications in which it's being currently used. I would say this field is about like 15 to 20 years old. So there are many very well established uh, protocols and methods and applications are emerging based on. One of the characteristics which I talked about, I'd like to tell you about is the ODMR, which is optically detected magnetic resonance. We are all familiar with the nuclear magnetic resonance. Here we do the magnetic resonance same way using optics. So basically using fluorescence. So this NV center has two states. When it goes from spin state from 0 to plus or minus 1 state. So it is a triplet A to triplet excited state, E state. So when it takes up the green light, it goes there and it goes to MS equal to 0 spin state, and it emits and comes to the MS equal to 0. So this is spin level matching, so it's a bright state. But it can also go to MS plus or minus state and comes to intermediate state and then come back to the bright state. So this we call it as the difference between these two states. This is we call it as a dark state. So when we can actually interfere with the microwave, you can detect between the difference between the bright and the dark state. So this is what here is it. The fluorescent counts and the microwave when we switch the microwave frequency, the fluorescent counts is the bright state, and when there's a dark state, that's a dip, and then it goes back to the bright state. So this is at there is no external magnetic field applied. So we can actually vary the magnetic field and see how the beautiful Zeeman effect is happening also, which I am not discussing today. So based on this principle, we make use of something like ASM, using which we call it as ND magnetometry, which is already commercially available in market by some of the companies, Tsunami. So what they do is this is mainly for the material science and the people who deal with all of reflection geometry study. For example, we have a small like this and a my push hook, and then you attach like a cantilever, you attach the diamond to the end, and then scan the surface, scan on the surface. So depending upon the location, orientation, and how the the domains of the particular material, you can see the by shooting the field, and you can see how the beautifully you can see the response from the system. So this is used for using mainly for ultrathin magnetic field, vortices, domain walls, and molecular magnets. So this is one of the applications using the NV magnetometry. So another application what we did was, this is from our group and we are in next line. We were trying to make a tabletop NMR instrument using NV diamond. So the first thing we would do was looking into the proton spin from water, pure water. So this was with two different NMR pulse sequence, with one to dynamically decouple and another one to dynamically sensitive control. We call it as DISCO, which was published a few years ago. And then what we do was take a slab of the NV center diamond and put water droplets on it, and then apply the electric field and looking into its various parameters. If you look into that, the bright and the dark state, and this is thing, and from there we calculate the Lama frequency, which is absolutely at 1.81 megahertz. We calculated, and we were able to come with the accurate number for the Lama frequency for the proton. And this is the graph, and this is the 3D which the representation of the how the contour looks over time, and this is how the sensitivity looks over time. This was done. So this gives us a confidence that yes, if we can see protons, then this can be used for multiple applications. And there are we moved from Max Planck to the company, and there are many labs which took up this idea, and they are developing more prototypes and more useful NMR tabletop NMR instrument. I think it will be in the market in a few years' time. So moving on to from like where you have a rigid NV center sensing application. Then we moved on to making use into fiber, which gives you flexibility in handling the NV center. So this was done with optical fiber. It is for multiplexing. So we built a NV-based flexible sensor. And then what we did was we miniaturized the fiber optic integrated sensor for multiplex sensing and simultaneous signal acquisition from several distinct spatial locations. Why this is important? Because when you have a cantilever kind of thing, you can only scan one sample at a time. But when you attach to the fiber, and many fiber can be used at the same time. So this is a fiber tip in which the gun was attached, and this is the various fluorescence markers, and this is the various view in which the fiber, different types of fiber, and the cross section of the fiber, and the tip in which the fluorescence is coming out of the green light was sent through the fiber, and the tip was with the diamond, and you can see the how to. So one of the major application we were doing is with the medical school was with to make use of the NV-based magnetoencephalogram. We all know about MEG and functional MRI and PET scans, particularly for the brain. And when we think about the spatial resolution and the time resolution, the NV-based MEG somewhere between the this current MEG and the functional MRI, so it's pretty good in that range. And why do we need such new instruments or technology? Because we have most of you have seen the conventional MEG, where we go to a special clinic or a room in which a big, which is all will have the squid kind of sensor, so which needs a cryogenic cooling, and in which you have to be, it's complex and big and messy and things like that. But when we move on to technology like with a fiber optic coupled with a diamond, then it is all, you can put various spots across the skull, and you can do it multiplexing at various points at the same simultaneously. So it has many advantages because it's at room temperature. It can be even taken to makeshift labs or clinics, things like that. So it has become like a point of care device. That's one of the ideas in order to where we are working with the medical school, in order to make it to more prototype and then go into commercial use. So far I said about sensing part. Now I move on to the what we do with computing in our company also. So, in order to understand the quantum effect, the basic principles, two of them is the superposition and entanglement. So, for instance, superposition, if I have to tell you about, let's take an electron and put it in a magnetic field in a spin particularly. And then it goes into state, spin up and spin down state, but it is not, according to quantum, it is not just spin up and spin down, it's also superposition of the two states. So that if you think about the classical computing in which we define bit, which is spin up and spin down, spin up and spin down, that's a bit. But if you go to quantum computing, it's the quantum bit, which is this qubit, which is not the spin up and spin down, it's also the superposition of the spin up and spin down. The other parameter is the entanglement, where instead you bring two particles together and they are connected by some means, and then you take them apart to the poles of the world, and then still they will be connected and they will be called the entanglement. So these two principles are major backbone of to see any quantum effect in any material. So if one pictorial way of saying how you see the classical computing and the quantum computing is, this is very analog pictorial way saying it, maze solving problems. For instance, most of us have played with the paper or electronically the maze, how we go out of the maze and come out of it. One of the big things in the classical computer, what is it? You put a mouse into the maze and then it goes, hits 0, comes back, there's no way, then goes and hits again 1, comes back and goes 0, 1, 0, 1, and somehow it finds a way and comes out. That's how the classical computer works, 0 and 1 bits. When you go to quantum, it has the eagle's eye view. Like it sits and sees the maze, optimized at multiple parameters, and it optimizes and it takes the least resistant way and it comes out much faster. This is one of the ways to say about the classical concept. So why do we need quantum computers? Do we need it? And quantum computing. So far, most of the quantum computing has been done with simulation using classical computing. That's a technology right now. But we are all coming up with hardware specifically for doing quantum computing. This is main because we all know this is a big data era where data is everywhere. You take it finance, you take it personalized medicine, or IT, or everywhere, education, there's a big data coming everywhere. So classical computers are struggling, even the supercomputers have reaching the point that they are struggling to handle such big data. So this quantum computers can mainly to take care of the big data problem and in uncovering patterns and spotting anomalies extremely quickly. So this qubits, they store two states 0 and 1 simultaneously due to superposition. I said you earlier. And they are very good at processing large data sets. Like we make use of like 2.5 exabytes of data every day. And this is the example I have given it from social media because usually I give talk to students. And then you can see how much, like even a small like on a Facebook like will create 4.2 million Facebook like will create this much of data in producing data. So it's not only handling big data, it also has the agent sees many parts and then optimize it. It can handle multi-parameter problems simultaneously. You can assign one parameter to each qubit and then do the computation simultaneously. So it can calculate something in seconds, which may take in minutes or hours to be done in the classical computers, and then in an energy efficient way. And it can also do multiple inputs simultaneously with multi-parameter optimization. These are some of the advantages of using quantum computers. So how the quantum computing with quantum computers will disrupt STEM industry? We all know all the science have become so interdisciplinary nowadays. So if we take into science and technology, chemistry, physics, math, encryption, computing, biology, these are various domains which, for example, if I take, as a chemist, I take a quantum chemistry problem, for instance, a climate with energy, which is going to have an interact from material science, from physics, which will have again various encryption code breaking from the math, and which is going to be in the computing problem, and again back to biology and things like that. Similarly, if you take a personalized medicine, then it will be obviously pharma and the biomolecules, which will have a lot of input from chemistry. Then it has to go to bioinformatics, which is computing problem. Then it goes to math, encryption, physics. So these are all like goes in bracket synergistic. So one will have effect on the other, and it gives back. So these kind of things will be very much uh, taken care by the quantum computing field in another 5 to 10 years, where there will be more application will be emerging in these directions. So talking about quantum computers, so far, like 5 years ago, most of the things were done using classical computers. We put the quantum code, including Gaussian packages, kind of thing. So what you do is you put your quantum codes into the classical computer and ask it to simulate. But now we have quantum computer hardware platforms, which is emerging, and they have offer each one offer its own unique advantages and distinct challenges. So I wouldn't say they are it's a mature technology like a classical computing. It's upcoming technology. It's the present. It's people have moved from prototype to the real computer quantum computer now, but it's developing. So it may take another 5 to 10 years to become like a more mature technology. But already people have started using it for various functionalities. So if you take, it needs to be taken care of. Material needs to have coherence time and operational fidelity, scalability potential, and technological maturity. The scalability potential here we talk about the physical qubits and the logical qubits, and this is what where everybody is trying to. There's a big quantum race going on there with the quantum hardware platform. Some of the five major platforms are one of them is conducting loops. One of by IBM, Google, and Rigetti Quantum are working on it. And you can use a trapped ion with a laser, and ion beam Honeywell are using on it. And you can also do with silicon quantum dots, and it's a very, very premature technology. Not many have started using it. And topological qubits, you can define qubits using topology. Microsoft is working on that technology. And this one is the diamond-based vacancy center body. Three of our companies, including us, working on it, defining the quantum hardware plan. So not only platforms, the choice of material, but it also how the quantum is felt from those systems. So three major classifications. One is the cryogenic, particularly superconducting silicon quantum dots. All this need really, really cold temperature in order to see the quantum effect so that the noise will be ready. Other one is in a vacuum, like a thermos kind of trap. Ion traps and neutral atoms need this kind of setup. So if you go and like if you're not familiar with quantum computer, just Google, say you can see a big picture of the room size picture kind of thing. But it is not necessary with room temperature quantum computers, where you can use photonics, that is with laser and various optics, you can define qubits. And our technology is based on the diamond spin of the NV diamond sensor. So we call it as the diamond NV spins as a qubit from nature because diamonds we all know it's also we can get it from mine. Um, that's also possible. So they offer a unique spin package, electron spin package in a solid state, offers functionality no other quantum system could match. And it is fully functional at room temperature, exceptional robustness, ultra small size, and minimal power consumption. As I said, it can be plugged in like a now like a desktop computer. You can also plug into a normal socket. You don't need very hi-fi infrastructure for this, except that it has room temperature, so even a AC running at 20 degrees is enough to operate this kind of quantum hardware. And compared to the pricing, it's very affordable and robust, and it is also secure quantum system understanding and testing. Not only as a computer hardware, it is also, you can use it as an onboarding with something else. So it fits very well. It is just, we take it in the back of our car, in the back seat of our car, we fit into, even we have taken in tram. You can see in our, some of our social media posts, you can see all this fun stuff we have done with that. And that, so it is that kind of integrable quantum processor is what we are. So what we do at XCQ GmbH, our motto is we want to democratize quantum computation because there's a big race there, and there's a big, it's not only just technology, it's a big business out there. So you have various ranges of people, things offering from different qubit structure, topology, and things like that. So at XCQ, we offer full stack quantum processor, which is energy efficient. And this is main idea is to enable quantum for widespread usage, not for only one sector of customers we are catering to. We want to have it a broad spectrum of customers, and which operates at ambient condition operation. As I said, this can be kept in a, like, it's like a size of a small fridge, the small size fridge, and bring quantum process in your personal space and robust and mobile. So this not only for putting your hands-on experience with quantum computing, but also it is for head start for innovators to move in that direction, so that you can define different languages, you can define different codes, you can do different algorithms, and it opens up a lot of global opportunities and challenges along with it. And moving on to some of the applications, what we are focusing on is secure encryption service for many markets. And as I said, quantum computers excel at multi-parameter optimization, like something like logistic and supply chain, finance and market prediction, some of them. And next big thing will be after AI will be the quantum AI, if quantum takes over. So it is, we are already working on model training and how the probability-based simulations on AI and neural networks. And with that, pretty much, I'll give you an overview about the sensor and the computing using the diamond-based technology. So it is green and sustainable technology. So if you look into that, we all understand the material is very important. So every day there is a material sciences coming up with a new micro to nano technology, novel materials, and smaller, smart, particularly environment friendly, because everybody is aware now we have to make things in a more sustainable future. So these things define what is the future of sensors. Not only that, if you use technologies like NVDFX, numerous ranging from brain computer interface to point of care medical diagnostic devices. So if you not only on the sensor field, our the diamond-based quantum looks very promising, and it's not only for us, so it delivers new tools and new knowledge, not only for us, for the entire humankind to benefit from it. So to acknowledge, I'm from XCQ GmbH. I'm located in Leipzig, Germany, where the headquarters is. This is our website, and if you're interested, you can email us for any queries. And our R&D lab, it's a R&D company which makes quantum processor and quantum computer based on diamond-based technology. So our R&D labs are in southern Germany, which is Ulm. It's a city in southern Germany. Our lab is inside the German Aerospace Center, which is DLR Quantum Computing Initiative partnership. We have a major grant from them. And most of the scientific work I discussed were done when the group was in Max Planck Institute of Multidisciplinary Sciences in Göttingen, Germany. And most of them are published from there. And we are generously funded by the Education Minister and Ministry of Germany and other many universities and collaborative partners. And with that, I thank you for your kind attention, and the floor is open for questions now. Thank you.
Thank you, ma'am, for your wonderful talk. Next.
Your questions, I am open to you.
Thank you, ma'am. Students, any queries, doubts? Okay, right. We can move on to the next talk. Introducing Dr. Brijesh Pare. It's an honor to introduce Dr. Brijesh Pare, eminent chemist, educator, and academic leader. Dr. Pare holds an impressive academic background with an MPhil, MSA, PhD, and postdoctoral fellowship, and he is currently serves as a professor and head of the postgraduate Department of Chemistry at Government Mahadev Science College, Ujjain, under Vikram University. With an exceptional 38 years of undergraduate and postgraduate teaching experience, Dr. Pare has made a significant impact on chemical education in India. He has served as a president of Association of Chemistry Teachers from 2020 to 2024, contributing greatly to national initiative in chemistry teaching and curriculum development. His research credentials include more than 90 publications in reputed international and national journals, Google H-Index of 17, and successful guidance of 21 PhD scholars, with several more currently pursuing research under his mentorship. Dr. Pare's area of expertise spans advanced oxidation process, photocatalytic degradation, green chemistry, and sustainable science, creativity, and critical thinking, and science education methodologies. He has been a panel member for the National Best Scientist, Best Chemistry Teacher Award, and has served as a resource person in workshops across India and abroad. In summary, Dr. Brijesh Pare is a visionary educator, a dedicated researcher, and an influential voice in advancing chemistry education, inspiring students and teachers across the nation. Thank you. I hand over the session to Dr. Brijesh Pare.
Thank you, Prof. And thank you, Professor Kavita, for giving this opportunity to speak on this occasion. And I shared it, so my presentation is visible. It's visible
Yes,
now?
sir.
I'm audible?
Yes, sir.
And its presentation is visible there, no?
Yes, sir. Visible, sir.
Okay, thank you so much once again. So I will not take much time. Thank you for this opportunity. And in the morning, I saw a wonderful inauguration program, and Professor Warner was there. So circular chemistry is the title. I wish to talk to the younger students today. And we all aware of the linear route, how these things are going on these days. We all talking about the green chemistry and sustainable chemistry, and then now to circular chemistry. So what has been the chemist has been doing, there are resources, then extraction, manufacturing, distribution, and the consumption, and in the last, that is the waste. So this is the linear route, the chemists have been following all through. Now, with the ongoing problems like climate change and resource diversity, and there's so many things happening, so the onus is on chemistry, that how to combat this situation and how to address all these problems. So the concept of circular chemistry is very, very interesting, just by expanding the scope of sustainability to the entire life cycle of chemical products. The concept of circular chemistry aims to replace today's linear take, make, and dispose approach with the circular process. That is the need of the hour. And this will optimize resource efficiency across chemical value chains and enable a closed loop, waste-free chemical industry. That is, everyone is looking for that. We all aware of that, the spending beyond income makes us bankrupt. Similarly, consuming endlessly on the finite earth can make us suffer miserably. This we all aware of it. So, the awareness of the finite nature of many resources, including the issue of the element scarcity, as well as the limited environmental tolerance towards our chemical industry has grown tremendously in the past few decades. So definitely the chemical industry is facing a huge challenge, to how to save the planet. And it has become painfully obvious that the linear route of production that I have shown in the earlier slide, in which the scarce resources are consumed and their value-added products are degraded to waste, is a root cause of the several impending global crises such as the climate change, the diminished biodiversity, as well as the food, water, and energy shortage. So it looks, like this leader. This is, picture probably you might have seen all, that showing the scarcity of the elements, in the coming years, because so much of extraction has been done, and some of the elements are very scarce, So sustainability is the main cause. Anyway, now everyone is looking for the circular economy, and what is the role of chemistry to enable circular economy, that we'll just see. So a circular economy is defined as a restorative and a regenerative by design, aims to keep products, components, and materials at their highest utility and value at all times. That is where the circular economy is. So chemistry is crucial for achieving this. Why? Because the chemists understand their role in designing and developing indispensable materials and technologies, but also simultaneously recognize the potentially detrimental effects. They are aware, the chemists are aware, that each step must be designed or reassessed with sustainability in mind. So that is where we are heading towards, and I will just give you some of the very good examples, This is circular economy anyway. So green chemistry for linear processes. That is, even in the morning, Professor Warner is the father of green chemistry, he very nicely discussed things. So I will go very quickly on that. So green chemistry has provided a framework for teaching and performing sustainable chemistry. And all the guiding principles of green chemistry, they focus on the direct sustainability assessment of chemical reactions and are perfectly suited for the optimization of linear production. The development towards a circular economy, however, require a re-evaluation of what defines a sustainable chemical process and needs to take into account the people, the planet, and the profit level. That is what we call the triple bottom line. This is probably we are aware of it. There is an environmental component, society, and the economics, and somewhere in between, there is a sustainability. So these are the things need to be taken care of when any kind of chemical activity has to be done. Okay. So the chemistry of sustainability recognizes that sustainability without innovation is impossible, and innovation without sustainability would be ruinous. So interdependent, these two things, because sustainability is definitely a new concept. And of course, the nature is quite sustainable, but the human activities are quite detrimental. Anyway, so these are the 12 principles of green chemistry. I'm not going into that because we are aware of it. I'll just go ahead. Okay, let us see, what is the difference between green and the sustainable and all. So there is one process, there is a process of the synthesis of adipic acid, which is a key component of nylon 6,6. And it has been done by the direct oxidation of cyclohexene with hydrogen peroxide. Earlier, it has been done, of course, at industrial level, it has not been replaced so far, but just by using nitric acid, which is quite corrosive, and while using the nitric acid in place of hydrogen peroxide, lot of environmental taxing gas like nitrous oxide was coming out of that as a product of the current industrial synthesis. That was a problem. Now, this green method, we know the hydrogen peroxide is a green oxidant, okay, and that is the requiring material in the new synthesis method for adipic acid. which means that this process is currently, and this hydrogen peroxide is costlier than the product itself, that is an adipic acid. So here that component comes, no, the economic component comes, and the reaction is a green reaction. You know, getting adipic acid by using hydrogen peroxide is a green process, but it is not commercially viable because of the cost of the hydrogen peroxide. And that is one of the things in sustainability. So this is a violation of value chain, okay? The root is green, but the accounting for the profit level of the triple bottom line is an essential component in the design of sustainable chemistry. So the method is green, but not sustainable. I mean, that doesn't suit to the design of sustainable chemistry. Similarly, one more example, you know, for particularly for the students and the new researchers, you know, this is the Haber-Bosch process. We all know about it. So this is a very good example, you know, where the nitrogen gets converted into ammonia and iron as a catalyst is being used. Okay, and then this ammonia is in turn used for the production of agricultural fertilizers. So it's a key industry showcase for the use of catalysts because iron is being used here, and increasing energy efficiency is also required. So the current process requires high temperature, no, and the pressure. So the green chemistry says that the reaction should be should take place at the ambient temperature and at the low pressures, and the further optimization has stagnated. Now see what is happening. This process, that is Haber-Bosch process, is a green process, okay? But what is happening after the use of the fertilizer? Large portions of the fixated nitrogens are lost to the environment, causing eutrophication. The global problem concern and the importance of which should not be underestimated. So this is what is happening, you know. So see these two examples depict very clearly that even if a reaction is green, it may not be sustainable. So now the chemists have to take care of this thing. Whatever they design, whatever new molecule they design, whatever is happening in the chemistry at industrial level, commercial level, it has to be sustainable. That aspect has to be taken care of. An increase in water and air pollution, both of which threaten to destabilize the Earth system beyond the proposed planetary boundaries or safe operating systems for the anthropogenic activity. This highlights the importance of looking beyond the scientific discovery. It is very important, and analyzing the global impact of chemistry using a systems approach. Now, so circular chemistry for sustainability. Now, so at this stage, you know, I think everybody now realizes that there is a need of a circular chemistry with a component of sustainability embedded into it. So there is a need to have a holistic view on how chemistry can contribute to the development of circular economy. I mean, how the circular chemistry can contribute into that. So Chris Slootweg, I would like to just name this professor from Netherlands. You know, they have done a very good work on it, and recently one paper on Nature has published on that. So this approach aims to make chemical process truly circular by expanding the scope of sustainability from process optimization to the entire life cycle of chemical products. It promotes, in particular, the resource efficiency across chemical value chains and highlights the need to develop novel chemical reactions to reuse and recycle chemicals to in turn enable development towards closed-loop, waste-free chemical industry. So these are the 12 principles of circular chemistry, quite in tune with what the 12 principles of green chemistry. That is what the team of the Slootweg have suggested. So the whole thing, the number one is the collect and use waste. That is the first principle. 2, maximize atom circulation. And there, you know, the word was used, you know, the atom economy, but here's a maximum atom circulation. You know, the material has to be to reutilize, you know. And third, the optimize resource efficiency. 4, strive for energy persistence. 5th, enhance process efficiency. No out of plant toxicity. 7th, target optimal design. 8th, assess sustainability. That has to be done, you know, after any chemical process. Apply ladder of circularity, that we'll see later. Sell service, not product. Another example. reject lock-in, and 12th, unify industry and provide coherent policy framework. So these are the 12 principles have been suggested for circular chemistry. So these again, these are all the description of these 12 principles. I'm not going into that. Okay. Now, what are the components of this circular chemistry and how it is going to help? So regarding waste as a resource, that is the first and the most important thing. I mean, any waste has to act as a resource, is a prerequisite for circularity. I mean, from where things have started from the resource to the product, the end product, and the end product. That is earlier the call as the waste should be the resource. Redirecting waste streams and using them as a chemical feedstock should become ubiquitous in the synthesis of marketable products in order to achieve complete recirculation of molecules and materials. Recirculation of molecules and materials. It is imperative to reduce uncirculated waste in any given process, and yet it will not be possible to eliminate degraded materials or products completely. So this was the concept from green chemistry, but the earlier one, that the complete recirculation of molecule is a circular chemistry. Waste management will therefore always be required for the effective circulation of materials. Okay, eutrophication and climate change are two of the biggest global environmental concerns, largely caused by the excess use of phosphorus and nitrogen-based fertilizers and the utilization of fossil fuels, of course. The excess of carbon dioxide, nitrous oxide, and ammonia and phosphate waste lost to air, water, and land perturbs the carbon, nitrogen, phosphorus cycles, creating a host of adverse environmental impacts. To reduce this impact of resulting waste products on the environment, novel chemical and biochemical conversions are urgently needed that allow for their efficient recovery and recycling. And in order to succeed in eliminating or reusing waste, an optimal process design is needed that allows for the efficient separation, purification, reuse, and recycling of waste products in an environmentally benign way. As we know, that the green chemistry case, the atom economical accumulated the synthetic efficiency of the individual state. In a similar manner, at the process level, maximizing atom circulation in chemical products along their entire life cycle. Now, another point, securing renewability. Circular chemistry seeks to replace today's linear take, make, and dispose approach with the process in which the materials are continuously cycled back through the value chain for reuse, thereby optimizing resource efficiency and preserving finite feedstocks. Okay, so renewable resources offer the chemical industry an opportunity to diversify its raw material base, but the greenwashing means, many times the processes are not as green, but they are just shown, green. So that should not happen. And bio-based materials are typically classified as being sustainable, simply because of and that is not the case all the time. That is not the case all the times, And this is an example, for a given application like the oil-based plastic or the bio-based plastics can be used, for example, PET or bio-PET produced from the monoethylene glycol itself derived from the agricultural products. Yeah, and both types of plastics are based on similar building blocks, and their function and properties defined at the molecular level are also all the same, So there is this kind of confusion is also there. Okay. Energy input is an investment. This should also take place. Using waste as a resource can also contribute considerably to the energy efficiency of a chemical product over its entire life cycle. And in order to repurpose waste material into a feedstock, it is important to achieve a recirculation of molecules and materials that ensure an energy economy. For example, carbon dioxide can be converted into a variety of other molecules like methane to alcohols to amines, which can in turn be used for the variety of purposes. But the conversion process should not necessitate more energy than that's offered by the product obtained. So that calculation has to be there. This circular chemistry, emphasize on reusability of material and as compared to the degradability. Yeah. The inherent reactivity that the control environment of chemicals enables their conversion into value-added compounds, but can also lead to adverse effects. In a similar manner to green chemistry, the circular chemistry strives to reduce the harmful impact of these compounds on the environment. Although the use of substances of concern may be unavoidable at some facilities, they should not be released to the environment. Yeah. No open toxicity. Toxicity not should be open. This approach requires the continued conglomeration of industrial sites and enhanced cooperation between the companies. Then product design. Optimal product design should target the most favorable end-of-life state. That is very important. Avoiding persistence in the environment and breakdown into harmful products. Yeah. Biodegradable materials are often seen as sustainable, yet the fact that the product can simply be disposed of in the environment may promote littering. Another issue often overlooked is that the microplastics, and the polymers partially degraded from a plastic bottle, they cause more harm to the environment than the original bottle. So that is also the issue. Again, following the green chemistry principles that encourages chemists to design material for degradation does not unequivocally lead to an increase in the sustainability, because that should not happen. That is the difference between green and circular chemistry. Therefore, rather than aiming for product degradation, it is preferable to collect waste streams and instead convert them into dedicated plants, into value-added materials. So degradation has to be avoided, and the reuse of the material with the value addition has to be done. Product stewardship, that has to be there. The circular economy relies on a decoupling of material consumption and economic growth. As we have seen, in sustainability, there are the planet, people, and profit. So to promote this, ownership of goods needs to be directed away from the user and back to the producer. This can be achieved by shifting payment models from ownership-based to the service-based system. This is one of the principles. An example is the use of shared cars. Yeah. One more thing, the circular chemistry producers are encouraged to use service-based business model. They call it the chemical leasing, to promote efficiency and longevity of the materials over the production rate and the quantity. And to shift the focus towards a value-added approach, targeting the service that is linked with the chemicals. For example, I would just like to a very successful example of this approach can be found in Egypt. ABB Arab is a manufacturer of electrical appliances who resolve high cost in electrostatic powder coating by collaborating with the fan and coating supplier Exo Nobel from somewhere around 2008. So instead of this ABB Arab buying the coating material per kilogram for their painting operation, the companies devised a process in which the expenses were charged per square meter of metal material coated, and the powder waste was returned to the Nobel for recycling. And the arrangement also included training of workers, resulting in the products of better quality and a reduction in the number of reject products, as well as the reduction in the maintenance cost. The resulting process is closed loop, generates no waste, and this ABB Arab saw a 20% reduction in coating used. So it's a service-based chemical industry is vital to circular chemistry, as the companies have the assets and the know-how to retrieve and repurpose chemical products, and the chemical industry is far better equipped to target the management of the molecule circulating loops. So this is what this circular chemistry
is going to do. Okay, so there are 12
RS, then I will just finish it. The letter of circularity is start from reduce, reuse, redistribute, repair, refurbish, repurpose, remanufacture, recycle, recover, and return. I mean, these are the things. I mean, it is yeah. This is a kind of a ladder, you know. Yeah, that is how it goes. You know, I mean, it's not okay. So anyway, with this linear economy, green chemistry has allowed the optimization of chemical processes, leading to the less environmentally demanding chemistry practices. In doing so, it has laid the groundwork for an environmentally friendly culture in the chemical discipline. So with this, the advent of circular chemistry, I hope, you know, like in the years to come, the chemistry industry will be looking more responsible toward the society, and all the, you know, the concern and the common problem of the globe, that is how the United Nations through the 17 goals of the sustainable goals, we are dealing with it. So hopefully the chemistry are going to contribute in a more significant manner through circular chemistry, and it will enable the circular economy, which is the need of the earth. Thank you very much. And I'm thankful to Chris Slutvich that this paper particularly appeared in the Nature Chemistry recently. Anyway, thank you very much. Thank you.
Thank you, sir, for your valuable time and enlightening session. We truly appreciate your time presence with us today. Thank you, sir. Next section, Dr. W.B. Gurnale, Visiting Professor, Department of Chemistry, RTM Nagpur, University, Nagpur. It's my privilege to introduce Dr. W.B. Gurnale, an eminent polymer chemist and a distinguished academician whose contribution has significantly shaped research and education in material science. Dr. Gurnale completed his MSc Chemistry in 1989 and earned his PhD in Polymer Chemistry from RTM Nagpur University in 2000. He served as a professor, head of the Department of Chemistry at Kamala Nehru Mahavidyalaya, Nagpur. Dr. Gurnale has made pioneering contribution in synthesis and characterization of nanomaterials, SBR nanocomposites, semiconducting materials, conducting and biodegradable polymer, TLC materials, and epoxy resins. With over 260 research papers in reputed national and international journals, more than 116 conference presentations, he is widely recognized in the scientific community. He is a reviewer for 54 international journals and holds 12 Indian utility and design patents. His academic output includes 32 books and 45 book chapters, and he has written more than 360 science articles for public outreach. Dr. Gurnale has guided 30 PhD scholars and 21 MPhil students, with several more currently pursuing under his mentorships. He has completed the major UGC-funded project amounting to Rs 86 lakhs. His excellence has earned his numerous prestigious awards, including the CRSI Best Teacher Award, Distinguished Scientist Award, and RTMNU Best Researcher Award, and the ISCAS Silver Medal. Dr. Gurnale has delivered over 90 invited talks, uploaded 350 online lectures, and represented India internationally in countries like Malaysia, Singapore, Indonesia, Thailand, Nepal, Taiwan, Hong Kong, and Bangladesh. In essence, Dr. W.B. Gurnale is a visionary researcher, inspiring teacher, and a respected ambassador of Indian science on global stage. I welcome you, sir.
Ma'am.
Good afternoon to all of you. First of all, I thank the organizer and especially the convener, Professor Helen Kavita Madam, for their invitation for this international conference. And today, as we know that the basic theme of the conference is the green chemistry or the sustainability. So I am working on the material science, and generally I give the presentation on the material, nanomaterials and different areas, epoxy resin like that. Today, with the theme of this conference, I am giving here the presentation on the climate change, and important topic is corrective action and what are our responsibility. So here, as we know that the backbone for sustainable development is the science and technology. Science and technology are different, but at the same time, they are very complementary each other. As we know, science is the pursuit of knowledge, and technology is the creation of artifacts for the people needs and making devices. As we know that the technology that makes our life comfortable are related to the materials, and materials are size dependent. As we change the size, changes the many properties of the material. So different kinds of materials are there: nanomaterials, luminescent material, biomaterial, biodegradable, polymer, composite. Number of kinds of materials are there. And as we know that we have to synthesize the material by using some green route of synthesis. So here, next. So in this presentation, I'm giving, we are going to discuss scientific technological advancement, various environmental issues, climate crisis and international policies, sustainable concept, various approaches for mitigation and duties and responsibility of individuals. Next. So what is the main thing is here, in this case, so many revolutions we observed: industrial, green revolution, white revolution, advanced material, life-saving, drug, medical imaging, communication, internet, dyes, cosmetic. So all these are there. These are advancement in the materials. There are all these kinds of material developments are there. The thing is that enhance the quality and so for our comfort life. So different kinds of materials are there, different kinds of things are there. So what is the industries or in the laboratories, we are working and doing the research on these topics and materials. Okay, next. So, so as we know that the chemistry play a very important role in the development for the sustainability, and we can say that for making the sustainable world. Okay, so here excessive use of chemicals we have to avoid. Harmful chemicals are there, toxic materials are there, chemicals are. So this slide shows what are the different kinds of pesticides we are using for the agriculture, and different kinds of medicines have been shown what we are using for our saving the life, and all these are the different kinds of materials. So excessive use of chemical for different purposes we have to avoid. Okay, next. And these are the some cuttings of the newspaper. So cocktail have been now banned. It contains some pesticides, and lead also. What is the is a heavy metal found in the soft drinks. So we have to avoid the drinking of soft these drinks. And what is the food adulteration nowadays found in some cases. 91 fruit traders also lose their license because of the carbide used for the fruits, and also soft drink can damage also sales. So all these are the cutting. So many workers, they have been banned materials, and now we are also using even the soft drinks like that. So these are the toxic materials we found, and also the what is the food traders also, they have banned their license. They have all these things are there, even that. So we should have to take care about this. So because last cutting shows that this soft drink also damage our sales. So there is a mechanism how they are damaging. So all these things are there. So next. And overconsumption of natural resources are there. So many resources in the natures are there. So we have to take care about the resources, and so different kinds of resources are there. As we know that so many resources are there we are using, but what we are giving to the nature, we are giving the waste. So, okay, so that waste we should manage. So proper management of the waste should be there. So all these have been shown here. We are destroying so many things. We are destroying the natural habitats, and also crisis levels are there. So what is now? All these things are there. We have to take care about our natural resources. Next. And in a year, 1 month will be there. In some villages, there is a problems of water. So this is the picture in somewhere in the village. And what is now, we found also, we see the news also, there is a problems of this. So in the year, and what is, they are going for the water for walking for 5 kilometers, 7 kilometers like that. So, okay, so this is, till now there is a problems. We have not solved this problem. Okay, next. So the important fact that 33% of the Earth's soil is already degraded, and 1 million species are now in the risk of extinction. And lifestyle has been changed now. It demands for more energy. Human is also extracting more and more from the nature and dumping large amount of waste and toxic substances in the nature, causing ecological imbalance at global and local level. So causing the many environmental issues. So all these are the facts are there. So we have to minimize the things, and we have to avoid some harmful chemicals. We have to manage. We have to properly using all these things, then it can be minimized. Next. So these are the facts. So number of issues are there, global issues, global warming, climate change, ozone depletion, acid rain, and these are the local issues. What is water, air, like that. So what is now here, I'm going to think on the climate change. How this is a major issue. Number of issues are there, but what is one global issue is the climate change. So why to care for the pollution and environmental issues? So questions are there. So many questions are there. Okay, but we have to give the solution for this. So as we know, there is a demand for the energy. So because energy needed for the development of the cities, development for the energy needed to do work. So what is for all these? We also require development, but at the same time we have to protect the environment. So, okay, energy is needed for doing the work for the different purpose. And also we need the development of the cities and other things. What is so? At the same time, we have to see where there should not be any more pollution. We have to manage the proper techniques or methods. Next. So energy sources are there. Initially, biomass, coal and oil. What is now? Today, coal and oil gas are there. In addition to that, nuclear, hydro, wind, biomass, solars are there. Now, as we know that different types of energies are there, but now in the future also, we are using now different kinds of energy for carry out the work. And what is now, as the reaction is shown, fossil fuel react with oxygen forming, giving the energy. So what is now, some garbage is there. So we have to manage again this garbage and that garbage contain more amount of the CO2. So day by day, the percentage of CO2 in the day in India, in across the outside of the India is increasing in a large amount. So this is the creating the problem. So GHG, that is greenhouse gas effects, are also causing these gases are more and more day by day. So why they are coming? So what are the how to minimize it? So we have to develop, we have to innovate some techniques or materials. So what is, we have also developed one material, we have synthesized the material and it react with the carbon dioxide and also minimize that. And another technique is, as you know that already the, what is the different types of gold is there. Gold you have seen using for the making the ornaments. And 3 more gold colors are there. Gold is golden color. 3 golds are there again. What is on that? Brown color if the size of the material is the 1 nanometer. If it is 20 nanometer, red color gold is there. If it is 100 nanometer, then the purple pink color is there. So different colors are there depending upon the size. One more gold is now been discovered, and use of that gold is to reduce the CO2 from the atmosphere. And I think that scientist is from the ICT Mumbai, and he has developed the gold. What is the name, color of the gold? You know that he received the Bhatnagar Award before 2 months by the hands of the President of India. What is the color of that gold? Is a black gold. So he used that the black gold concept, black body concept, and developed that material. So main use of that material is to reduce the CO2 from the atmosphere. Next. So here is shown in this slide. China is having in the year, what is that, 27%, 0.2% total, more is the top one to emit the CO2 in the atmosphere. The second number is the, what is the 14.6 United States. Third number is our India, 6.8%, and remaining rest of the words are shown. So see here how much CO2 coming in the year by different ways, and here is the graph is shown. So this is the global issue, major issues are there. And next. So we should have to maintain the carbon cycle. It is very important to balance the carbon and to maintain all these things. So carbon cycle should be maintained. As we know that slow process, and here is the fast process. And thing is that carbon dioxide, when react with the water in the presence of light, what is, we get the sugar and oxygen is there. Okay. So we should have to maintain this carbon cycle. If it is not maintained, I think you know that there is no carbon, then what is, the things get frozen, what like that. So what is, we should have to maintain the complete cycle. This is the important part. Next. So in this case, this table shows different types of component, water vapor, CO2, methane, all these gases are there. What is now, but CO2 in the ppm, what is, here is given pre-industrial concentration shown in ppm 280, concentration in 1998, 365, day by day it is increases, see now here. And so it is the problem of CO2 because of the emission in the air and from the different sources. So the increase of CO2 in the air and day by day, so what is the causes the change in the temperature, and therefore what is the global warming is there, and if there is a global warming, what is the climate changes are there. So if there is a climate change, what are the climate changes? If the temperature rise by 1 or 2 degrees, what is then temperature in Canada is shown here. What is the, it is, Leeton is the city where 49.6 degree temperature is observed. These are the effects of the climate change. And what is, so see the red area is the high temperature range shown in this graph. Next. Because of this climate change, what is now the fire for, what is the, in the forest also, they, what is this, collapse, what is the, strikes each other, the, what is now then, we get this fire. And this year also we see the fire in case of US in California near the forest. What is, so automatically they get now, because of high temperature, the fire we found in the forest. Next. So flood is also observed. We have seen in our India also, in Himachal Pradesh, in also Nepal, in also in Japan. So many no control is there because of these changes in the climate. Next. Another effect, melting of ice cap, and therefore what is now, this is the polar bear also in a risk because the Antarctic ice is also melting. So all these are the changes we observed because of the climate change. and so many species, microorganisms are there, number of species are there. They are also now missing from that, so we cannot find all these species, and this NASA have given. Another thing is that sea level in Indonesia, Jakarta is the capital of Indonesia, and now what is the sea levels now, as the temperature increasing, what is now the water from the sea is coming in the what is the capital of Jakarta, and now because of that Jakarta, their capital have been shifted from this place to another place, so it is not possible. So in future also such type of problem comes. So all these are the problems because of the climate change. Storms also we have found, just now in Chennai also came one storm, and every year 2-3 storms are found. So all these are the problems, all these are the issues are there, and because of the climate change. So what is now the Indian air quality we should have to maintain? When the quality is when it is the one up to 50 or less than 50, then it's good. And see, all complete is given color and category and range. And what is the severe hazardous situations are there? As we know, the situation at present in the Delhi also very what is the situation is bad. Very what is the air quality index is very high, and therefore they have some problems. Many problems everyone is having. No one, schools have given the holidays, and also they are giving education through online, and so many office also doing work from the home like that. So situations are there. Same situation may come in other city also. Next. So this is a slide show conversion between present and future generation. Now he is a small son, and his father is there. His father is saying that here, son, I save all this money for your future. So remember that what is he saying? That son is saying, what is use of this wealth? He stored complete wealth for his son. Everyone is doing like that, parents. But now what is the use of that things, wealth? What is, if there is no pure oxygen, we cannot get the oxygen. We cannot live without oxygen. If there is no oxygen, then what is the use of this big amount of money or like that? Okay, so this is the thing in future, that this time this like this should not come. Okay, so like that, so we should have to maintain the oxygen also level, maintain the environment. Next. So who are the creators of such type of problems, and who will solve the problems? So we can say that we are the part of problems, therefore we must have to give the solution for that. And here we are inhabitants of earth. So as we know, in short, climate change emergency demand action from all of us, and we need to go to zero GHG emission by 2050. Everybody has to play a role, important role for this case. Okay, there should be zero emission of that GHG. So here important quote is given by the Dalai Lama. We are the generation with the awareness of great danger. We are the one with the responsibility and the ability to take steps of the concrete action before it is too late. So this is the spiritual leader of Tibet and Buddhist teacher, and he says that who will initiate the concrete action? Everyone in the morning also speaker said that who will give the solution? Who will give the innovation for the sustainable? We have to develop the material, we have to give solution. So who will start? So he is also saying who will initiate this concrete action? Who will give the solution for that? Now, as we know, constitutional fundamental rights are there. Our fundamental rights and some duties are there. So right of the freedom, religion, equality, pollution-free environment. We are enjoying our rights. Everyone is enjoying the rights. But now what is, if someone denying our rights, the fundamental duties are there. So are we aware of our we should have to know what are the fundamental duties. So here, the Constitution of India, Part 4A, in Article 15(1)A, fundamental duties have been shown, and two important duties here: to protect and improve the natural environment, to develop the scientific temper, humanism, and spirit of inquiry and reform. So these are our duties. So we should have to take action. We should have to protect our environment, and we have to perform the duties. So here, sustainability concept play a very important role. And what is the sustainable development? Development that sustain in the future. That should be sustained in the future. Here, so for this improvement in the lifestyle, well-being, and preserving natural resource and ecosystem. They in three important parts are there: economy, social, and environmental. So when we carry out this one, when we sustainable development is the key success in the modern world. Without the environment, the development will not sustain. And in the modern world, development is equally important. So both are development and sustainability, both are equally important. Next. So these are the 17 goals of sustainability, as we have seen, and some initiations have been shown here. In 1972, UN conference was organized in Stockholm regarding the human environment. In 1990, US Congress established the Pollution Preservation Act. In 1992, first Earth Summit is there, and outcomes of this is shown here. Agenda 21 action plan is there. Blueprint for sustainable development for 21st century is the outcome. UNFCCC formed in 1994 stabilizes GHG emission and protect the earth from the threat. All these are there. Acts are there. And what is the outcomes are there. So what is now? But we are not implementing. In some cases we are not implementing. So in case of scientific climate agreement, some agreement is also there. What is the, we say that Kyoto Protocol and Doha Amendment, Paris Agreement. So all these are to reduce the gas, to minimize the, what is the global temperature, their discussion. All these are the important climatic agreements to reduce the CO2. So what are the India's initiation now? For this, the limit emission intensity per unit is GDP by 33 to 35% of 2005 level. And India aim to reach 40% of the installed capacity via non-fossil fuels. By 22, India target 175 gigawatt of renewable energy generation, and India set a goal to increase forest cover to absorb 2.5 billion tons of CO2. So plantation should be there. Each and everyone should have to do the plantation so that the CO2 can get absorbed. Next. So some here approaches are there for climate change mitigation. So one is the use of solar energy and restrict the power use. So nowadays this thing is going on in the houses also. The solar panels we are using, and now in the future also nano solar cells have been made by the scientists, and now our bus, our train, our majority of the automobiles will be work on this nano solar cell like that. And this is the one alternative. In case of energy, as we know that in the future energy, what is three energies are there. One is the solar, wind power, solar power, and what is the wind power. All these are the three important in the future we are going to use, and that is important. So shift our dependence of these sources, renewable sources. So here is shown same thing. What is here? Decay organizing, the fossil fuels are there, carbon dioxide, reactive water, we get some sugar and oxygen already shown. But here is now how these CO2 cycles work, organic carbon, and here is the plant respiration. So plant give what is the give the oxygen, take the CO2 like that here. In this way, so the process is going on. Next. So this is the carbon cycle. Non-sustainable and sustainable path is shown. Photochemistry, and here is industrial biotechnology. So this cycle consumes good and fuels. So we require sustainability path. Next. So energy efficient technology required, and this is the one method, microwave heating. So this is one of the compound N-phenyl benzamide. When react with the reaction is carried out, and when it is keep it for the 12 minutes, we get the benzoic acid. So this is the microwave heating method. So in this way, we should have to develop our methods for conventional heating procedure. Takes 18 hours, but this takes very short time to convert into another material. Next. Ultrasound assisted synthesis, another method is there. So in this way, the reaction can be carried out and we get also octane to give the ketone very short time, and also the yield is very much more, 92.8%. So yield is also increases. So such type of challenges are there, but develop the more energy efficient technology. So another method is there, more energy efficient technology. Next. So we can also use the catalyst. Again, if we use the catalyst, then we get the more product and in a short time. As we know, catalyst, different kinds of catalysts are also there. And so this using catalyst also, we get the product in short time. Next. So photocatalysis is also one of the solar, because the solar sun is available, and therefore we use this one. And this is the natural photosynthesis process shown here, and artificial photosynthesis also can be carried out. So both these natural and for here the artificially also possible, and we should have to develop such type of methods. Next. Development of this artificial tree is shown here. This photocatalysis is an important approach to address the carbon neutrality and also some of the environmental issues. So artificial photosynthesis is very important and should be carried out in the future. Now the scientists are also working on this part. We are also synthesized in a laboratory. This is the graphited carbon nitride, and this is the compound we have synthesized, and the paper is also published in Catalysis Science Technology. And here this compound react with the carbon dioxide and break down the strong bonds and convert it into the hydrocarbons like methane, like that. So this is useful material to reduce the CO2 in the atmosphere. Next. So different kinds of study we have carried out about this carbon CO2 photo reduction activity. Possible mechanism is also been here. So all these show the what is the use of this phenyl graphited carbon nitride. Next. I'm going fast. Here is the mechanism of CO2 photo reduction is shown, how it works, how it react with this carbon dioxide. Next. This is the cycle, how every materials are giving, what is the CO2, develop closed reactor which convert CO2 to the fuel. So in this way, the fossil fuels, car emission, gases are there, energy, fuel, chemicals are there. So by using the photocatalysis, it is also possible to photo reduction of the CO2 and convert into another part. Next. So this is another method that we can reduce the CO2. We have to minimize by converting the CO2 into the CNT. CNT is carbon nano CNT, carbon nanotubes, and also oxygen is emitted. So here we get oxygen, and also CO2 can be minimized, and we get the important, these are the reactions shown in this case, how the reaction is going on here. She shown. Next. So these are the green synthesis of nanomaterial. Some green route of synthesis of materials are also there, and in this case show instead of using toxic chemical, instead of using some other materials, chemicals, what is microorganism, plants, different part of the plants, laser heating, hydrothermal, sonochemical, all these are the methods. As we know that traditional methods are costly, not eco-friendly. Therefore, we have to use the green route of methods of synthesis for nanomaterial synthesis. So this is important. And what is there is no any, these are eco-friendly, and so these green methods we have also used. We have also published the paper. We have taken the medicinal plants, their leaves, their stem, like that, and so we are extracting some nanomaterials, silo nanomaterials, zinc nanomaterials, metal oxide, like that. Next. And this is the one simple method is there. First of all, these are the different steps. Take the leaves of the plant, then cut it into small pieces, heating it in a hot plate, then aqueous leaf extract is there. After that, silver nitrate solution we have to mix, and we have to stir for that. Leaf extract and the silver nitrate we have to add, then stir the magnetic stirrer and formation of silver nanoparticle. Then after that we have to characterize. So this is the simple here. The complete steps is shown here. This is another what is the graphitic carbon nitride with the thiopene dicarboxylic acid. We tried different types of compounds with the carbon nitride. Next. These are the different studies of this material. What is the electrochemical capacity behavior? So this is also shows the good activity for photo reduction of CO2. Next. This is galvanostatic charge discharge plots. Next. This is silver oxide microsphere with the carbon nitride also being shown here, and also this paper is published in Applied Catalysis of an Environment. Next. Next. So I'm going fast. Next. Some what is the photobacterial performance also shows this compound carbon nitride, silver oxide, and they show very good activity in the bacterial sites. Next. Some modification of the existing process are there in case of R&D, and already we know that tragedy in the Bhopal union carbide was there. Methylamine and react with the phosgene and give the methyl isocyanate, which is very poisonous, and tragedy was there. So this is the conventional old method where the in Bhopal tragedy is there. What is? They give the carbaryl And now new method, green process, phosgene react with the 1-naphthol. What is then we get chloroformate ester and with also with the carbyl. So what is now, instead of conventional method, we have to develop another new method for the same compound we get in this way. So innovate a new process having less, we should be a less hazardous and the toxicity. So this is the alternative method for the synthesis of same compound. Next. So prevention of waste and byproduct is there. So first method is, just example is given, reactant A plus B, and we required energy and solvent, but we get the product. But what is now toxic byproducts are there, waste. But in another, we have to develop such method. Reactants are same, but now we are getting the product, but there is no any waste. So we have to develop, we have to invent such type of process where there is no any waste material. Next. So in 2021, Nobel Prize in Physics have given to the scientists, and they on the work of their climate modeling, human effects on global warming. So on this also topic, they have received the Nobel Prize. And only scientific approach for climate mitigation is not a work. Heavy consumption and human greed is the important part and fundamental cause of pollution, ecological imbalance, climate crisis is also is there. Next. Ensure sustainable consumption. So fashion is there, but use the consumable material fabrics. It should not be damage the environment. Next. Billion dreams are there, but one planet. What is? In an ecosystem, finite resources, there has to be a finite consumption. The earth has enough resources for everybody need, but not enough for everybody greed. Climate crisis are the consequential impact of the heavy consumption and human greed. Next. Use water wisely. As we know, water is very, to drink water is very limited sources are there. So use water wisely. Do not waste water. Okay. So all these are given here. It is very important. Next. Use the food also wisely, because in the functions we are taking much more in our plate. It's good food, so taking, but after that we are wasting also half of the food. Okay. The things are good, foods are good, so we are taking. So take care of when we are eating the food in functions, in birthdays or in the marriage and like that. Okay. So avoid that one. Take the food as you required. Okay, that much. Next. And transform or transport. So many issues are there, local and global. So suggestion is that 70 people are going in 17 vehicles. So much rush is there, much fuel is also consumption is there, and much thing are there. So what is, instead of that, for that, what is one bus for 170 people? So we can use 2 buses for 140. So one bus is sufficient. So we save the fuel, we save the what is the here fuel and other things. Also we reduce the pollution like that. Okay. So this is the suggestive remediation for that. Next. So plant more number of trees, take care of them. So don't plant a tree and after planting take the care. Okay. So this is very important. Otherwise, some are doing the plantation in college or in some other institute, but after 1 year, after 6 months, no one plant is there. So take care about the plants. And next. So this is the plantation drive. They planted, but no plant was there after the 1 month or 2 months like that. So not only on the paper. So this is a dream scientist here. He says that luxury and lives have huge maintenance cost, but truth and simplicity are self-maintained without any cost. So this is very important quote given by the Professor Abdul Kalam, scientist. Next. Our environment, the world in which we live, and work is a mirror of our attitude and expectation. This is given by the Earl Nightingale, American radio speaker. He has given, this is taken from the Human Character and Development shows here. Next. So in the last, changing the climate, so many issues are there, and we should have to develop a method. We should have to give the solution for the better and also give the solution or give the material to reduce the pollution or to reduce the CO2, which is responsible for the climate change, and because of global warmings are there, and because of climate changes are there. So, and so many issues are there. In general, what is, give the innovative method, give the green method, give the new material for to minimize and make the world sustainable. And we know that chemistry play a very important role to make the world sustainable. So for so many things are there. Okay, so This is the, these are the issues, environmental issues are there. So what is now? We are the creators, so we have to give the solution for these issues. So I stop here. So some have been, suggestion have been given, modify the way of our celebration. As we know, in 2019 report of CPCB, what is 1,25,000 tons of waste is generated during the Holi. Somewhere they are cutting the trees and burning the trees, okay, like that. So do not stop burning like that. Celebration turning to rowdy and dangerous, okay. Festival become commercialized now. So don't make it commercialized. Thank you for all of you for the your attention. Thank you to all of you. If any question, you can ask. Anyone? You are the creator of the issues. You have to give method. You have to give solution. You have to give any innovative method. Okay? So these are the things. Okay.
Thank you, sir, for your inspiration session and has broadened our perspective and encouraged us to think critically. Your words will certainly motivate our students and faculty going on. Thank you once again, sir. I request Dr. Prabhu, sir, to honor Dr. Kurnale, sir, with the memento and certificate.
Yeah, small announcement. So everyone should assemble outside the auditorium, refreshment. Poster presentation students, so be ready for your posters. I kindly request Dr. Gurunali sir and Dr. Pawar sir to evaluate the poster. After the poster session, everyone again should assemble in the TRB auditorium. So our campus life students will be performing very vibrant cultural performance.